Hello, Devox. My name is Luka,
I'm Geoffrey.
and we are here to talk to you today about optimizing the world for fun and profit.
Yeah, so the world is full of scheduling problems, of planning problems. And I just took the train in Ghent at 7 a.m. this morning, and I arrived here at 3 minutes ago. So I can really tell you the world is full of scheduling problems, especially with the Belgium railroads, right? So, and it's about maintenance scheduling there. But just to give you an idea, if you walk into the airport, for example, let's take a look at how many planning problems we actually have there. So you walk in and you take the train, you take the escalator to the departure hall. Well, what you actually see in front of you is a maintenance scheduling problem. The escalators need maintenance every X amount of weeks, and that needs to be scheduled, and hopefully not while you're actually arriving there and need to catch your plane, right? You continue further, you check in your luggage at the check-in counter, and of course, there's a planning scheduling problem there too. As you can see, the employees need to be assigned to shifts, and so they're actually there to take your luggage. But there's also a desk scheduling problem, because the airport needs to decide, and the airlines need to decide which desk does which airline, and and for each airline, which desk is for which flight. So now you continue your journey. You look at the departure screen. What you will actually see there is another planning problem, namely your flight scheduling. Okay, you have a number of flights there. What time do they leave? That's a typical airline problem, of course, to decide those flights.
But it's not just an airline problem, right? It's also about runways.
Yes, indeed. It's also an airport problem, because they need to make sure they have enough runways to actually let these flights take off at that particular time. You continue your journey, you walk through security, and of course we have another shift scheduling problem there, right? This has some interesting constraints, like for example, you want one of each gender there for frisk searches and so forth. So you have interesting constraints in some of these variations of shift scheduling. Now you continue your journey and you go to the gate, and over there we have again a shift scheduling problem, right?
Yeah, but some of these people at those gates, they're the same people we've seen earlier, right?
Yeah, and so they need enough time to actually get from the check-in counter to the gate between their two, shift parts, to put it like that, right? So, okay, there's aircraft on at the gates, of course, and so scheduling these aircraft, what particular aircraft an airline will use, is again a planning problem. It's aircraft scheduling. And of course, those need maintenance. So every 48 hours, they need Class A maintenance. Every 8 days, they need Class B maintenance. And all that maintenance needs to be scheduled, and hopefully before you need to depart. And like I said this morning, for trains, that was actually the problem. So, and if it's not scheduled in time, then of course, the passengers face with the issues, right? And of course, there's a gate scheduling problem. Which gate takes which aircraft?
Yeah, and that problem is not actually as simple as it seems, because not every aircraft fits to every gate. For example, the large aircraft at the back, the Lufthansa one, the Airbus A380, they had to rebuild entire airports just to fit that monster in. So some gates can only fit some airplanes, and sometimes there's even not like an actual gateway. Sometimes it's just a bus. So yeah, there's plenty to schedule there as well.
Yeah, and then you board your plane, and over there you have again you see another planning problem, namely the pilots and the stewards. They all need to be scheduled, and all of these is a flight crew scheduling problem. So yeah.
So how does the flight crew scheduling differ from like the normal employee scheduling?
Yeah, it's a good question, because in a normal in a normal shift scheduling problem, you don't have to figure out where people are. They will just show up in time and leave in time. Obviously, if you send somebody from, let's say, Brussels to Los Angeles, their next shift cannot be in Brussels, right? Cannot start in Brussels. So you have to take into account in which city or which part of the world they are, right? So, the world is full of scheduling problems. This is just one of them. Walk into a train station, you'll see it doesn't. Walk into any company that does logistics or anything like that, you'll see another 10, 20 planning problems once you start looking out for them. And it's a lot of fun to actually optimize them. So some of these problems are automated. Sometimes they have something in some. Most of these are actually done with human planners, but some of these are automated with systems, but very few of those systems are actually optimized with advanced algorithms, right? So what we're going to show you is how you can optimize them with Java in AI, with AI in Java, right? So let's take a look.
Right. So first, let's maybe talk a little bit about whether or not optimization is even worth it. And I want to use an example to demonstrate this, which I believe we've all been through not too long ago. Remember 2022? This is the chart showing the gas prices over the past few years. And that spike in the middle of the chart, that very, very high spike, that's August 2022, August last year. And when we, back where I come from Czech Republic, when we saw that, there was a lot on our mind. Specifically, we panicked. Because suddenly, because the winters get cold where I'm from. And when there's no gas, it means that people are going to freeze. And it means, apparently, that also there's going to be no electricity because those power plants are powered by gas. And next year, there's going to be no food to eat because apparently fertilizer is made from natural gas. So, or using natural gas. So for a while, there was a lot of panic where I'm from, but the reality actually turned out to be a little more different because we adapted. What you see here is the chart of actual gas consumption adjusted for weather. So weather has no effect on these charts. The red line at the top, that shows you the gas consumption in the year 2021. And the blue, which is constantly below the red line, shows you the gas consumption in 2022. So what you're seeing from this graph is that we've been actually able to reduce our natural gas consumption by 15% adjusted for weather and all the other effects. And we did it by turning the thermostats to the left and not heating buildings at night. So there was some impact on quality of life, but we actually managed to do it without converting any power plants to solar or wind or water, because there simply would have been no time for that. So as a stopgap solution, we just turned the thermostats to the left and we managed to save 15% of natural gas just like that. Now, as I said, this was a stopgap solution. So surely we can do better because we have the technology now. So imagine if we could optimize for efficiency gains to get those minus 15%, minus 20, minus 25, without making those sacrifices on quality of life. It is possible now. We have the technology, and we are going to show you how it works and how to use it. Geoffrey?
Yeah, so let me just give you one other example and show you what kind of optimizations you can get out of that. So this is a vehicle routing problem where we need to send a number of vehicles to different locations across the country. This could be, for example, to deliver items like parcels or to pick up parcels, but it could also be to do some service there, like field service technicians installing, fixing things in your street or fixing things in your house, right? So there's many, many use cases of these. But there's a whole bunch of, so just to give you an idea, there's a few, for one of the cases that's well known is, for example, they expected, for a big company, they expected a 1% less driving time. Now, if you have tens of thousands of vehicles, reducing the driving time of all of your vehicles by 1% is a huge deal. It literally saves you millions, right? It was less than 25%. It reduced their results by 25% less driving time. That actually resulted into more than 10 million kilograms of CO emissions per year. To give you an idea, that's flying from Brussels to New York 25 times per day, right? So the overall cost of that over a year, that's the same amount that they actually reduced simply by doing the math better, the algorithms better, right? And it also saved them a few $100 million per year. So there's some of these use cases are extremely interesting to just optimize, and others actually give other benefits. So why is it so difficult? Yeah.
So Geoffrey, why are these issues so difficult to solve?
Yeah. So no, actually, it's yours. Go for it.
Yeah. So yes, we are going to be showing you, just for starters, don't worry, it's going to be harder later. We are going to show you, just for starters, a school timetabling problem where we actually have 4 different time slots in our school. We have 2 rooms, we have 2 hours to schedule, so we have 4 time slots. And we actually have 4 lessons to put in those 4 time slots. First lesson is math for 9th grade, taught by Mr. Alan Turing. Second is chemistry, also for 9th grade, taught by Mrs. Marie Curie. So as you can see, those 2 share the same student. The third lesson we want to schedule is French, also taught by Marie Curie, but this time for the 10th grade. So the yellow one and the blue one, they have the same teacher. And the final lesson we want to schedule is history, taught by Mr. Indiana Jones, for 10th grade. So as you can see, the blue one and the purple one, they have the same students again. So let's take a look at how we could do that. We take our solution, we take our problem, we throw it into some kind of an algorithm. We'll discuss the algorithm a little bit later. And the algorithm actually gives us a solution. So Geoffrey, what do we think about the solution?
I think it's good, but I think it's fairly easy to get, right? That wasn't really hard. We had 4 slots. We tried some combinations. Yeah, looks good.
Yeah.
What's so hard about it?
So the hard part is that we actually have some constraints which are not so easy to put together. So let's take a look at first solution that comes to mind. And this solution, well, Geoffrey, what do you think about this solution we have right there?
Yeah, so you mentioned earlier the room conflict constraint, the students and so forth, all right? This one is obviously a bad solution because you can see that we're putting 2 lessons in the same room at the same time, French and math. That's not going to work. So this is a bad solution.
That's very obvious. So let's not talk about this one anymore. We've got a room conflict, that's very clear. Let's move on. What about this one?
That looks good. Let's go with it. Perfect. Problem solved.
Are you sure?
Yeah, why?
Take a better look. How about the 9:30 part?
So chemistry and French. So chemistry and French, they're both taught by Marie Curie. Can Marie Curie be on 2 places at the same time?
Nah, she was good, but not so good.
Yeah, okay.
So maybe we have a problem, and we can see that problem from the teacher view. Teacher view shows it very clearly. We have math and history taught by different people at the same time, so that's good. But French and chemistry, unfortunately, taught by Marie Curie at the same time, so this solution's not going to work. Let's try a different one. We have a teacher conflict. Let's try a different one. Geoffrey?
Okay. You got me last time, right? So let me check this one. Can anybody see what's the problem with this one? Maybe math and chemistry, they're both taught to the 9th grade, right? So same set of students. So that's not going to work out there at the same time.
So in the teacher view, we see that things are clearly right. So let's take a look at the student groups view. And indeed, we are asking student groups to have 2 topics at the same time, which again is not going to work. So we have a student group conflict. And let's try a 4th solution. Geoffrey?
There were only 3 constraints, right? Rooms, teachers, and students, so should be fine. Looks good.
This one's good?
Yeah.
Okay, so finally, after on our 4th attempt, we got a decent solution.
Yeah. Oh, let's go to the left.
What happened? Okay, yeah. But maybe this is not like the ideal way to visualize it, and Geoffrey is going to show us a better way.
Yeah, so we actually built a web UI, so we can actually nicely show you what the results of our algorithms is. We'll show you what the algorithms are in a second, and we'll use that UI to actually just test if the schedules look good. So you can see a solve button there on the top left, we're going to use that to solve with whatever algorithm we have. And then on the top right, we're going to check it per room, per teachers, or per student group as a view to just make sure that they work out correctly, right? So just to give you an idea of the architecture, we've created a REST service. We've chosen to use Quarkus here. That could have been Spring Boot 2, of course, or any other technology you like. And we have a demo UI written in JavaScript. It's just a simple one, very simple one. And we send some test data to there, so it can actually show something, so it can work with something. We can generate the test data in different sizes, so we can see how this thing scales out later on. And then what actually happens, and this is the important thing to understand, the UI sends the problem to the REST service, it solves it and sends it back, right? And this is how we test our algorithms to see if they're any good or not, right? So now, what do we send back and forth? What's in that JSON file we send back and forth? Well, those just get parsed through Jackson. So these are actually the domain classes in Java, right? And so we have a time slot class and a room class. So the time slot says, for example, it has a day of week, like Monday, Tuesday, Wednesday. It has a start time and an end time. Start time could be like 9 o'clock, end time 9:50, or start at 10, end time 10:50, right? And of course, we have beyond the time slots, which were the rows, we also have the columns, the rooms. And so the rooms just have a name here, like room A, room B, and room C. In a more elaborate example, you might keep track of the capacity of a room, right? But in this simple example, we'll not take that, we'll not add that complexity. Now, you also have lessons, right? So each lesson has a subject, like math, French, chemistry, right? And each lesson also has a teacher, like Marie Curie, Alan Turing, and so forth. And also each lesson has a student group, like the 9th grade, the 10th grade, or here in Belgium, that would be, you know, at Eerste Middelbaar, something like that, right? So the question is, of course, now you might see that the teacher and the student groups are strings here, again, because we kept it simple. In a more realistic example, in a more elaborate implementation, you would probably have a teacher class and a student group class with a whole bunch of properties on there, like, for example, when the teachers don't want to work and things like that. But that's out of scope for this demonstration. So now we have the domain classes, but we also need to figure out if it's, you know, if the solution we generate is any good, right?
Yes. So in order to measure the quality of the solution, we're actually going to use something which we call the score. Sometimes you get to sometimes you get to hear about it as an objective function. We'll call it the score. The score is a number, and the higher the number, the better the solution is. In our case, we only have hard constraints. So for every of those impossibilities, like sharing the same time slot and the same room at the same time, we are going to add actually -1 to the score, making it worse. So as you can see in this very simple code, it's just 2 for loops iterating over all the lessons in pairs. And we make sure that there is a penalty whenever 2 lessons share a room and a time slot, a teacher and a time slot, and a student group and a time slot. We put all those numbers together, and the resulting number is the quality of the solution. Ideally, it's 0 when no constraints are broken.
Yeah, so a higher score is a better solution, basically.
Yes.
Oh, that's simple. So I have a brilliant idea. I have a brilliant idea to solve all of this.
It's good that we have you.
So it's the greedy algorithm, right? And so the greedy algorithm works like this. I think it's perfect. Let me just show you. We start from an empty schedule. None of the lessons are actually assigned to any of the slots, right? And then we have 4 slots. So we take one of the lessons. I'll take math here as an example, and we just assign it to one of the available slots. So we try the first slot at 9:30, room A. We try the second slot at room B at 8:30. The third slot, room A, 9:30, and of course the fourth slot, room B at 9:30. We score all of these. All of these are fine. There are no conflicts with other rooms with other lessons because there are no other lessons, and we just pick the first one.
Yeah, looks good.
Okay, and we just continue from there. We actually do the same with history, right? But we leave math where it is. So we try history at the first slot, and then history at the second slot, and so forth. You can see four cases again. Now, if you can see here, room A at 8:30, we now actually have a room conflict, two lessons in the same room at the same time. So obviously that's a bad idea. So we'll just take the next one, which is fine, right?
You sure about that one?
Yeah, well, what's wrong with that decision?
Yeah, let's continue.
Okay. So, okay, next one is chemistry. Now, chemistry has actually the same students as math, so we need to make sure doesn't happen at the same time as math. Beyond the room conflicts constraint. Now you can see the first two solutions here actually have a room conflict constraint, but actually both of them also have the same students conflict, because if you would chemistry on 8:30, math is already at 8:30. So actually two good reasons in both of these cases not to take them. So we just take the third one, right? Okay.
Yes.
And then we continue, and the last one is actually quite simple because there's only one spot left to put French. So we put French in there, and there we go. We have the optimal solution.
Yeah, but is the solution correct though? It looks very much like the first solution all the way back. That was a problem. We had the Marie Curie problem, you remember?
Oh, so yeah, chemistry and French, they actually have the same teacher.
Yeah.
Okay. Maybe this algorithm isn't that brilliant as I thought it was.
Yeah, it's even worse than you thought, I think, because the solution was already impossible in step 2.
Over here in step 2?
Yeah.
Because we still had to place chemistry and French, which have the same teacher, and we only had spots left at the same time. So we were doomed at that point already.
Yes.
Yeah. Okay.
Not a very good approach. Maybe you're not so good.
Fair enough. But I still want to investigate it a bit further. I want to show it to you how this works, right? Because I think it's an interesting algorithm. I think we'll need it later on again. Just maybe, get some improvements on top of it. So this is the algorithm. What we basically do is we do one big for loop across the lessons, and we assign each lesson to a time slot and to a room after we do some calculations inside that loop. And so what's the calculations inside that loop is basically we try all of the time slots and all of the rooms, right? And we check if the score if we would assign that particular lesson, it's just the last lesson we're assigning, all the others are written in stone already. If we assign that, what the score is, and if the score is better than any of the others for that particular lesson, then we keep that so we can set it at the end again for that particular lesson, right? So, you want to see a demo?
Yeah. Let's do a demo.
We're here to do demos, right? So, here we go. Let me switch to presentation mode, and I really like to have my bar at the top, so here we go. And we're going to close these for a second. So we have the greedy algorithm here. That's the one we'll be looking at, right? So let's take a look at this one, right? And let's open 12. Here we go. And I'm going to go into that one, create timetabling, and I'm going to just start that, and we'll take a look when that starts up. We have some properties we can play with that. I'll show you in a minute. That's actually in the application properties. We can play with the number of lessons we schedule, but we'll need that in a minute because let's first try it out. So here we go. We refresh. Okay. This looks weird. We refresh with Control F5. It looks better. So we have 4 unassigned lessons, the same lessons as we've been showing earlier. We're going to press the solve button and solve it with the greedy algorithm I just explained and the code I just explained. And let's solve that. We get a score. Looks good per room, right? Every room, no room conflicts, looks good. But the score thing, right?
Yeah, we see that there is one constraint broken somewhere.
Yeah, let's take a look per teacher. Okay, per teacher. Okay, Marie Curie, 2 places at the same time. Yeah, but okay. Yeah, but for the students, it's fine. So
she's a troublemaker.
Okay, fair enough. So let's take a look at now. Let's take a look at how long this actually solved, right?
Yes.
So what you see is this took actually 0 milliseconds. That's a rounding error. It took longer than that, right? So what happens if we actually increase the data set? Because we don't just want to be able to solve this for full lessons. We want to solve this for for 20 lessons, for 400 lessons. The average high school the average school has 400 lessons, right? And then you have much bigger schools and smaller schools. So you want to be able to deal with more than just 4 lessons. So I'm going to just ramp this up to 20 lessons just to show you what happens. And we're going to refresh this. And then you'll see we have 20 unassigned lessons. We're going to press the solve button. And as you can see, it solves them. Again, it's very snappy, right? Very quickly. And what you can see here is we have, so the rooms look good.
Teachers look good.
Yeah. Student groups.
Oh, and we have a student group conflict.
Yeah, over here, right? And you can see that's why we have the -1 score, right? So again, we have the same problem. Greedy got us quite close, but not all the way, and it's really not a schedule we can actually put in production, right?
And how long was it solving for?
Yeah, good question. Let's take a look. 15 milliseconds. Only 15 milliseconds.
Not bad.
Yeah, just
for a bad solution.
Yeah, okay. So, greedy, algorithm, fast, scalable, no problem but going to 20 lessons from 4 to 20, but far from optimal, right? So, yeah, maybe a little bit useless, but okay. Do you have a better idea?
Yeah, I do. I do have a better idea. It's more my street. I call it the brute force algorithm. And what the brute force algorithm is going to do is it's going to start exactly as the greedy algorithm started. It's going to evaluate every branch for the first lesson. So we're going to have 4 branches, but where it's going to be different is that for each of those 4 branches, it's going to evaluate every single one of them for the placement of the historic class. So it's 4 branches out of every of the 4 branches. And then it's going to do the same thing again for the chemistry lesson. Once again, all the branches from all the previous branches. And finally, it's going to do the same thing for the French class. So it's gone from all the branches of the math class, through all the branches of the history class, through all the branches of the chemistry class, to all the branches of the French class, until finally we've got the full picture, all the possible solutions. Some of them we can clearly see are wrong, like for example the first one, bottom left. Some of them are not obviously wrong, but they're still wrong, like for example the one that says we have a teacher conflict. We have the same teacher, Marie Curie again. But there is one at the bottom that is feasible, and that's the one we want. I declare victory. We have found our solution.
Yeah, nice.
It is, unfortunately, with a code like this. So we have to iterate over all the lessons once, and then over all the rooms once. That's for the first set of branches. Then we do a nested, then we nest these loops for the second set of branches. We nest them again for the third set of branches. And we will continue nesting and nesting and nesting until we resolve all of the n branches. So obviously there are better ways of writing this code, but fundamentally there's going to be a lot of iteration.
It's basically 4 loops all the way down.
Yep, 4 loops all the way down.
Now, yeah, you can't really write this code because the n is probably dynamic, so you don't know it at compilation time. But there's ways to write this code properly quite easily, right?
That's just basic computer science.
Yeah.
So, let's do a demo.
Yeah.
Let's cancel this thing.
Yeah.
Why doesn't it? Okay. Yeah. Let's switch to the brute force directory. Forgive me while I battle with the Belgium layout. Let's run Quarkus dev like that, so that I don't need to type.
Okay.
And it's going to be starting up for a while, so let's switch to the browser. And hopefully we...
Well, let me help you.
Yeah.
Here we go.
Yeah, thank you very much. So we are back to where we started, but this time with the brute force algorithm. So let's click on solve. Let's see what happens. It's doing things, and we've got a solution.
Yeah, is it perfect?
Let's take a look. It's got a score of 0, so it better be perfect.
Yeah.
The teacher view looks good. Student group looks good.
Yeah, great. It took a little bit longer, right?
Let's take a look at how long it took. It took 5 milliseconds,
Well,
but
okay. That's
it was
fine.
actually a good solution. So yeah.
It's probably just the UI going a bit slower. It was actually just the UI actually going a bit slower. Can you do me a favor? I want to see how this scales. So we're still looking at the properties from the greedy algorithm. Let's take a look at those from the brute force one.
Yes, I'm gonna open the brute force ones.
Yeah.
Resources, application properties.
Yeah, let's also switch that to 20.
Switch that to 20.
Yeah. Let's see how that works out.
So we reload.
Yeah.
Okay, now we got our 20 lessons.
Yeah.
Let's click on solve and we should see the results any second now. Okay, 5 milliseconds over.
Maybe it crashed. Can you take a look at the
yeah,
log?
sure. Let's take a look.
Huh?
Brute force started, it says. So it's doing something. Should we wait?
Well, let's do some math around this. Let's leave it solving
Okay,
for a while.
I'll leave the math to you.
Yeah. Okay. Thank you. How many nodes are there here? Anybody have an idea? Right. So let's do some of the math around this. So in the first choice about putting the actual math lesson in there, we have 4 ways to do that. 4 nodes, right? In the second choice to put history in there, we get for each of these 4 nodes, we have 4 nodes to put history in. That gives us 16 nodes. That's actually times 4. So once we start adding in chemistry, the third lesson, we do this. We multiply this by 4 again, and we're at 64 nodes. And then when we add the fourth lesson, we get to 264 nodes. So it's 4 times 4 to the power 4, right? So what would happen if we get 400 lessons like the average school, right? Well, 400 lessons like the average school will give you the number of combinations will be 10 to the power 1040, so n to the power n. And you're probably wondering how big is that number? Just throw some cloud computing at it, that will work. Just to give you an idea how big this number is, how big do you think is the minimum number of atoms in the observable universe? So think about every grain of salt, any breath of air, any atom on any planet out there in the solar system. Yeah?
A lot.
Yeah. So it's actually 10 to the power 80. So this, for 400 lessons, it's not 1,000,000 times bigger. It's literally like Google times bigger or something like that. It's it goes beyond human imagination, basically. So, okay, brute force, right? So let's take a look at how long this would take to solve with brute force. Now, depending on the machine, this machine it was faster, but on one of the benchmarks we did, we came around 8 milliseconds to do brute force for 4 lessons. And for 5 lessons, it took 1/10 of a second, right?
Yeah, that's all right.
Yeah. For 6 lessons, 2 seconds. Yeah. For 7 lessons, it took 170 seconds.
I can grab a coffee or something.
Yeah, sounds good. 8 lessons took an hour.
Yeah, I'm not watching it anyway.
Yeah, okay. 9 lessons took a day.
It's in a cloud, right?
Yeah. 10 lessons, it took a month.
Okay, that may be a problem.
Yeah. 13 lessons, it takes 2,000 years. That's about when Voyager reaches the next nearby star, to give you an idea. 15 lessons, it takes 2 million years. That's when the Apollo bootprint fades on the moon, right? 17 lessons, that's when the sun explodes, right?
We're not gonna need any schedules by then.
No. But we just started 20 lessons, right? So how do we want to wait for that, or
Maybe not.
no? Maybe not, right?
Gas is still expensive.
Yeah. So let's actually just close that down, right? So here we go. We jump here, and we're actually going to close that down as we can't wait a few billion years, right? Here we go, and let's go up one directory. The brute force algorithm, you want to compare?
Yes, so we've seen it's slow. We've seen it does not scale at all. But when you get the solution, it's good.
So you don't get a solution, but it is optimal. Right?
Yeah.
Yeah. Okay. Sounds like we're in. You can have your cake or eat it too, right? We want a little bit of both. So let's actually take a look at more advanced algorithms, right? And some of you probably at this point are thinking, can we not use all this new AI stuff out there, right? So I'm going to do a quick intermission before we continue on this, because we left out a piece.
I thought like we forgot something. Yeah.
So let's have a quick intermission just for the fun of it. So DevOps scheduling. So for years, DevOps has been scheduled with Optoplanner, right? And so earlier this year, I woke up one morning in March, and we were working Optoplanner, and now we're working on the continuation of Optoplanner called Timefold. And so early in March, I woke up and all of a sudden I saw Stefan Janssens, who's the organizer of DevOps, post this on Twitter. That he basically said, I have replaced Optoplanner with ChatGTP, right? With GPT-4, and there was a link to the results, and you could see how he does it, right? And so, that was a scary morning to wake up. I looked at the results. He had some good results. There were some hard constraints broken, but there was much promise in there. And over the next few days, he actually got better and better results. So I figured, let's make a bet around this. So I just challenged him to a bet, right? So you want to bet that ChatGTP, so GPT-4, even with bigger data sets, there were new versions coming out, will actually still not be able to solve the DevOps scheduling problem. And I actually made a clear bet here. If you can find a feasible solution for a schedule for DevOps Belgium with GPT by October, it doesn't even need to be optimal. I will dress up as Duke to welcome DevOps attendees the entire week. And so Stefan had a real strong vision around that. This was his vision, which was fun, right? Until, of course, 2 months later, DevOps UK came around, and he actually said, I can generate a schedule for Voxed with GPT, right? And you can actually see the schedule he's generated there. And so he declared victory, right? So that was a bit of a scary moment for me. I'll admit.
So where's the costume?
Yeah, good question. So I actually asked for a feasible schedule. Doesn't need to be optimal, right? And so let me explain to you what a feasible schedule means. It means that no hard constraints are broken. So give you an idea, what are the hard constraints in a conference scheduling case? Here, this is the DevOps schedule, as you can see. There's a bunch of deep dives in there, talks in there. That's the yellow ones. There's a bunch of conference talks in there. And each little cell is actually a square, is actually one of the talks that's happening, right? And the constraints in there is that every talk has to be in one room. You cannot have two talks in the same room at the same time. So again, the room conflict, which is fairly easy to solve. You just make sure they all end up in a different room. GPT can do that very, very easily. And then you have hard constraints like the speaker unavailability, but there's not that many, right? And then you have speaker conflicts. Now, speaker conflicts means that a speaker has two talks at the same time. And you also have speaker pauses, which means that when a speaker has two talks, they shouldn't be back to back, right? And I figured, well, that's going to be the big issue for GPT to solve, because I was actually during that day when I placed the bet was doing something with school timetabling, as we shown earlier, and there for the teachers typically have 20, 30 lessons in a week, and it's really hard to get that right together with the room conflicts. But do you know how many talks the average DevOps speaker has? It's more or less one, right? So that basically means, maybe two, that basically means the speaker conflict isn't really that big of a deal, right? There were a few other hard constraints in there, prerequisites, crowd control, I won't go into them, but they're not really that hard. So feasible is actually easy. It's doing optimal that's hard. So optimal means things like we want to deal with content conflict, where we don't want to have two talks about the same topic at the same time. We want to deal with same-day constraints, with track conflict, so you can always go look at all of the talks about mobile or something like that. Room stability, so you can predict the room. Intros first, and then more and more and more. And there's a whole bunch more, and there's actually been new ones being added this year. So anyway, like I said, my mistake was I asked for a feasible schedule, right? So when I realized this, this happened. So, and it turns out it's actually very hard to rent a Java Duke costume. There's like one in the world, right? It's not like you can just rent one down the street. But I had one hope. I said find a feasible schedule for Devox Belgium, not for Voxed, for Devox Belgium. Right, so what's the difference between those two? Well, Voxed is 30 sessions, and Devox is 210 sessions, right? So is it just 7 times harder than Voxed, or as you've now seen in the brute force slides, is it more something like 10,000 to the power 365 times harder, right? And obviously it's the second now, right? So Act 3, in August, Devox, so Stefan and Devox said on Twitter that they're actually using Optoplanner, which is now Timefold, to actually generate the schedule. So victory!
When you say victory, Geoffrey, I had to wake up while it was still dark outside to be here on time for this presentation. Does it seem like a victory to you?
Yeah, 9:30 Monday morning, maybe not a victory, right? And this is our own algorithm that scheduled us here, right?
Yeah,
so
no exploits there, no exploits.
No, maybe should add some. No, just kidding. So, is it really a victory over generative AI? Well, if you actually looked at some of the talks, you will actually see that there's still not something perfect in there. For example, there's 2 Spring talks at the same time. And actually zoom in, what you'll see is that the tags there are no tags in common. So there is a constraint in the solver that says if 2 talks have the same tag, we would like to avoid scheduling at the same time, right? And it has a certain weight, and it will try its very best to accommodate for that. But here it didn't see that those 2 talks were actually on the same topic, simply because the left has a talk called Spring Boot, and the right one does not have that talk. It has Spring Boot 3.0. So clearly, it just scheduled those at the same time and thought everything was fine. Now, there's ways to fix that. What Stefan is actually playing with is from GPT, you can actually generate extra tags based upon the title and the abstract. You can then put those into the talks, and we can then use that in the solver, the Timefold solver, to actually make sure those talks don't happen at the same time. So generative AI and solver AI actually do work well together. Which brings us back to the advanced algorithms, and we can continue on remember where we left off. We had greedy, which was fast and scalable, but not optimal, got bad results. We had brute force that gave the optimal solution. You just have to wait a few billion years or longer for it, right? So, can we have our cake and eat it too? Well, there's a whole bunch of advanced algorithms, and specifically for these kinds of problems, vehicle routing, employee scheduling, maintenance scheduling, satellite, bandwidth scheduling, and so forth, meta-heuristics are really a good choice. Now, we'll just go over the top of some of these algorithms. Actually, one of these algorithms, the local search algorithm. Just know that this is the tip of the iceberg, not the tip of the icebergs, and there's many more subsystems, advanced subsystems below us to get these working quite well. But I just want to give you an idea how they work. Like I said earlier, the greedy algorithm is actually quite interesting because it's a good starting point. It's extremely fast, and it gives you it gets you somewhere along the way already. So we'll actually take the output from the greedy algorithm, the math, the solution here, where chemistry and French are actually being taught at the same time, and we'll start from there to do what's known as local moves. So what is a local move here? We take one of the lessons and we try to put it at a different spot. So for example, in the first case here, we take the lesson room A at 8:30, the math lesson, and we move it to 9:30. In the second case, we move it to room B. In the third case, we move it to room B at 9:30. And all of these, as you can see, actually have an extra broken heart constraint. So here, chemistry and math are now in the same room, and you still have the chemistry-French problem. And you can see with the red lines there that all of these have 2 heart constraints broken. Now, one of the moves actually just moves the history, French lesson to 8:30, which does break 2 lessons in the same room at the same time, but unbreaks the constraint that chemistry and French cannot be taught at the same time. So Marie Curie is happy with this, but the students in the room is not happy with this, right? So basically, we take that one and we continue from there with the algorithm, and there's some probability in there and large number games in there. And again, it's far more. This is just the tip of the iceberg. But from there, we again continue with making moves. And as we evaluate the next set of moves, you'll see that one of them actually leads us to the optimal solution, right? And we do this through a number of steps as the problem gets higher. Now, here's an interesting to see is we don't get the brute force nodes that we always have a single path that continues. So it actually scales very well. So do you want to implement this yourself?
I'd rather not, or rather I had to, but maybe you don't need to.
Yeah. So there's actually an open source library to use this. It's called Timefold. And
Good one.
Timefold
That's
is
the one.
Yeah, so Timefold is a continuation of the Optoplanar project. It's a library of optimization algorithms. It's AI but not ML. It's not machine learning. It's open source on the Apache license. And it's actively developed by our open core company around it to continue it, right? So does it work? What about the compatibility? It works with Java, as we just shown. It works with Kotlin out of the box. We actually have quick starts that show you how to use it in Java, how to use it in Kotlin, and we're working on a Python version 2, which is just a wrapper because under the hood is actually still Java, because Java is very, very fast, right? So you can use it with plain Java, just embed it as a Hello World quick start you can use. You can use it with the Quarkus extension, so that does some of the stuff for you. You can use it with Spring Boot Starter that does the same stuff for you, right? There's examples, there's quick starts, all the quick starts have Maven enabled, and 3 of them also have Gradle enabled, so if you want to see how that one works. And it works on all platforms as Java, it works on all clouds as Java, right? It works locally on your machine. It's just an embedded jar, right? So what we're going to do in this architecture, we're just going to add the Timefold extension in the Quarkus thing here. And but we need to tell Timefold, okay, what can you optimize? What can you change? Can, for example, Timefold say, I'm going to change the subject of a lesson, or I'm going to create more time slots? Obviously, it can't, right? So what we're going to do is we need to tell them that the time slot and the rooms, those 2 fields here, that's the 2 fields that it can actually change. So we add a planning variable annotation on that, right? And that lets the solver know these are the things I can play with. And the class that has those annotations, those fields with those annotations, that's the lesson class that actually needs a planning entity allocation, an annotation that basically says to Timefold, this is the class that has fields that you can change, and then it can find the planning and variable annotations in there, right? So before solving, these fields are not filled in. After we give it to the solver, it will actually fill this in for us.
It will first fill them with the result of the greedy algorithm, and then it will improve with all the smart stuff we've shown.
Yep. So, but you still need to tell it what to do, right? Just like we had to do with the other algorithm. So if you remember earlier, Luka showed you the score calculation. This is pretty much the same code. It will look very, very much the same. So what we do again, we go through, this is the easy score calculator. What we do is we take 2 for loops to actually find any pair of lessons. We check if the room and the time slot are the same. If not, we reduce the hard score. We check if the teacher and the time slot are the same, reduce hard score if so, and we check if the student group are not. So again, we check our 3 constraints. The only difference is we don't just return the hard score, we actually wrap it into a hard and soft score of the hard score and 0 because no soft scores is broken. This will allow us to introduce soft scores later on, soft constraints later on by actually splitting those up nicely.
And you should notice that we actually iterate over all the lessons. We do that twice. And please remember that because that's going to be more important later.
Yeah. So there's a reason we call this the easy score calculator. And yeah. So let's do a demo of that. So let's switch back here. Let's do the same thing again. Here we go. Starts up. Let's switch to over here. All right, and let's refresh. Okay, so we have our 4 lessons, which we showed earlier with the greedy algorithm and the brute force. When we click the solve button, it actually solves these. And just like brute force, it actually solves it optimally. So 0 hard, 0 soft, so no constraints broken. If we look at by teacher, you will see it's fine. Marie Curie only has to be at 1 place at the same time. And student groups also fine, right? So brute force could do this too, right? And greedy could not. But let's take a look at what happens if we now actually scale up to more lessons. So we go to the application properties. Here we go. We bring that up to 20 lessons, like in brute force. Do we have to wait 1,000,000 years to see the solution?
Hopefully not.
No, hopefully not. I don't think we have that much time left when you look at the monitor. Okay, here we go. We have the optimal solution for 20 lessons, right? So you can see all good per lessons, all good per teacher, and all good per student group, right?
Yay.
Yeah, and you can actually also see here in the node how long it took. It took about 22 milliseconds. So that was quite fast, right? So, oh, and let me shut that down for later. There we go. So, algorithm comparison. The meta-heuristics are, local search is a form of meta-heuristics, are fast, they're scalable, and they're near optimal.
Yep.
So the reason that they're not near optimal and they're not optimal but near optimal is because they will actually take the amount of time you give them to solve it. So once you start scaling out to very big problems, not just to 400 lessons, but things like 10,000 visits, find the optimal solution for vehicle routing to deliver to 10,000 visits in a number of days, you will find that no software and no computer power on the planet can actually give you the optimal solution. So it actually works the other way around. It asks, how much time do you have? Do you have a minute? Do you have 5 minutes? Do you have an entire night? Do you have an hour this night or 4 hours this night? And based upon what you give it, it will give you the best possible solution it can find as near optimal as possible. And that's really big advantage in the real world. So, ChatGPT, well, before we go into about the GPT stuff, let's talk about the humans. How good are humans? Right?
They're not bad, actually.
Yeah, they're actually very good at small problems, but once it gets a bit harder, right? Think about when you were in school and the teachers had to figure out the best schedule for the school. For us, it literally took 3 weeks before they find a schedule that actually worked, right? I remember sometimes not having a lesson simply because they couldn't find a feasible schedule. And basically, how do they solve it? They hire more teachers and problem solved, right? So just as you increase your costs, that's also a way to do it. Now, why is that? Well, humans are not that fast. They take a few hours to actually find a solution. They do scale. They can handle big cases, but they're actually far from optimal. They're actually very much like the greedy algorithm. It just doesn't take them a few milliseconds. It takes them a few minutes or a few hours, right? And even if they if you give them days, they don't get much better than the greedy answer. Maybe slightly, but not that much.
So does ChatGPT do that?
Yeah, so let's take a look at how good is generative AI, stuff like that. Well, and this is an opinion, this is from some of the data points we've seen, and again, we'll see how this rolls out over the next few years. But as we saw with what Stefan also generated directly from GTP, it was fast, questionably scalable, but it was far from optimal and typically did not deliver a feasible solution. Now, what's actually interesting about Stefan's story is that he will actually manage at some point to have generative AI generate the code to generate to run the solver, right? So you can actually ask ChatGPT, for example, to generate some timefold code, and it will generate you a whole bunch of constraints, or with Copilot. It's also quite interesting how it actually sometimes reproduces the exact comments that I really like, the ones I actually wrote in the original examples. So it's quite interesting to see sometimes. But that's all good. The problem with that is that you never know if it really generates the right constraint. And so you want to have generate some unit tests on top of that, and you want to be sure that you're really solving the business problem, what they want you to solve, and not something what most other people solve. As well as you want to, sometimes it just doesn't compile. So there is interesting stuff in there, but that will work out over the next few years. So a quick architecture overview before we go further. Basically, we just talked about the left part, the solver. How do I find a better solution, basically, right? And that's where the algorithms. And so we've gone through this, shown you what algorithms works. Now we need to start talking about the right part, is how do I calculate the score of a solution efficiently? And the left part is stuff we can handle for you. That's what our open source library can handle for you. It's the right part that we can support you with, but we cannot tell you what your business wants. You need to tell us what your business wants, what your organization wants, and so forth. So that's where we basically need your input, right?
Yes.
So let's start talking about constraints. Before we show you how to implement it, I want to get a few concepts into your heads. So the first thing is positive and negative constraints. Okay, so here we have 3 possible solutions that come out of our algorithms, and the algorithms needs to know which one of these is better, which is the one you would like us to take. And in this case, we want to maximize apples. So what do you guys think? What is the best of these 3 solutions? What do you think, Lucas?
The one with the 5 apples, right?
Yeah, more apples is better, right? So what we're going to do is we're going to formalize this into numbers because computers need to be able to compare stuff. So we're going to every apple is 1 point, and then you can clearly see the right solution has 5 apples, and that's the highest number versus the other numbers. So that is the optimal solution. It's fairly simple, right? Okay. In this case, we want to minimize fuel stops. We have 3 vehicle routing cases where we're sending vehicles across the country, and that consumes an amount of fuel. So the question is, which of these 3 solutions is better? Anybody have an idea? What do you guys think? What do you think, Lucas?
The one on the right again, the one with the least fuel stops.
Yeah. So how do we formalize this? We basically say every fuel stop is -1. That's why we also did minus on the hard constraints earlier on in the lesson scheduling. And so when we sum this up, we will see on the total left -3, -2 in the middle, and -1 on the right. So the optimal solution is again the highest score. That's very handy, right? That we always have the...
Also very easy.
Yeah, higher is better. What happens if you want to, harvest apples with tractors and you have a vehicle routing problem around that? So here we have, again, 3 solutions. Let's presume that one apple is worth same as 1 fuel stop.
Yeah, fair enough.
Yeah, maybe not in most countries, but yeah. So what do you think, Lucas? What is the best one here?
Well, we've got 2 apples at the right, that's the most apples, and we've got 1 fuel stop on the right, that's the least fuel stops. So the one on the right?
Yeah, indeed. So how do we formalize it here? We say, okay, an apple is +1, the fuel stop is -1, and you can see that then, of course, the one there is the highest number, and that is the optimal solution. So this is a way you can combine positive constraints with negative constraints. Now, in reality, most constraints are negative. It's really like you shouldn't be doing this in your schedule, and you shouldn't be doing that in your schedule. But there's a few notable exceptions where you do need positive constraints at some point. And so by doing it this way, your system will still work once your business starts telling you need to add these. The next step is score weighting. One apple is not the same as 1 fuel stop, I might add, in the real world. So in this case, we have 2 things we need to take into account. We need to take into account driver happiness, driver retention, otherwise we lose our drivers, and that's really bad. And of course, we want to minimize our fuel stops. So the business has decided that 1 unhappy driver is as bad as 2 fuel stops. So when we have to choose between 1 fuel stop or 1 unhappy driver, we will choose for 1 fuel stop, basically. So the question is, from all of these solutions, which is the best one? What do you think?
Now I actually have to do some counting, right? So I see no unhappy people in those solutions on the right, so let's start there.
Yeah.
That's 0 for the unhappy people, and then I've got 1 for each of the fuel stops, so the one bottom right, that's the best one.
Yeah, so what we basically do is we say the unhappy driver is -2, the fuel stop is -1, so then an happy driver is weighted twice as much as a fuel stop. And then we just do the math on everything, we get a number. So for example, here on the top left, we get to -7. Why? -2 times -2 for the unhappy drivers, that's -4, and 3 times -1 for the fuel stops, and together -4 plus -3 is -7, right? And so clearly, again, this is the best number, this is the highest number, so there we have our optimal solution. So this is how we do score weighting. Now, you might think that score weighting is very important, right? So here's the problem. When we talk to the business developers implementing this, they often have a problem with their business because there's multiple stakeholders there. There's a stakeholder that says we want to reduce profit as much as possible, right? Typically coming down somewhere from the CFO or organization like that. And then there's a stakeholder that says we want to increase customer satisfaction or driver happiness because that's what their targets are, right? And of course, the whole company also wants to reduce ecology for their reputation, right? So you can actually have multiple things you want to weight upon, right? So here's just one advice I'd like to give you all. If you use a uniform focus with traditional algorithms, you will, for example, get these results, right? And if you would then focus on profit, you will actually gain some profit at the expense of the others, right? Of course, you can focus on any of the other sides too.
Just a second. What do you mean with the traditional algorithms?
Oh yeah, that's the greedy algorithm I showed earlier.
Okay,
right? That's
yeah,
typically
right.
what you will find in production, or what if humans are still doing this, that's typically what you will find. Now the interesting thing is, when you start using advanced algorithms, this is that you will see a win-win situation for everybody. And again, after the win-win or during the win-win, you can start saying, I'm going to focus specifically on profit or on ecology or customer satisfaction, right? And that, of course, depends on the company as to what are their major goals are, and how do they weight these against each other. But the general advice I'd like to give you as developers, if you implement any of these cases, is try to get out of that discussion, right? So put some numbers on it, implement your implementation, and then at the end, make sure in the UI they can say, okay, I want to put more weight on profit, or more weight on customer satisfaction or ecology, right? And they can see the results from that in the UI as they send them to the solver. And because it can really be a parallel analysis thing if you start doing that in the beginning of the project. Okay. Now, beyond score weighting, there's a third concept. So we had positive and negative constraints, we had score weighting. There's a third concept to understand, and that's score levels. Because basically, if you do a vehicle routing problem and your axle breaks down, right? Yeah, you put too much weight into the vehicle, and the vehicle simply doesn't move anymore. Then it doesn't matter how much fuel stops you have.
Yeah, it gets you in trouble with the law, having overloaded axles.
Yeah, you break down the roads, and good point. So that basically means that one broken axle is infinitely worth number of fuel stops. So out of all of these solutions, which is the ones you would actually want to put in production?
But we're looking for some of those that have no overloaded axles, right?
Yeah.
So it's going to be some of those on the right.
Yeah.
The one with the fewer fuel stops?
Yep. So basically, we put two numbers on everything: the hard constraints broken, broken axles, and the soft constraints broken, which is the fuel consumptions. We always look at the highest number first, which the hard constraint number first, which means indeed, like Luka just said, the ones on the right, and then we can compare there the soft score, and then that's where we have it, right? So shall we try this out?
Yes, sure.
After the break.
Okay, so let's meet back here in 15 minutes, everyone. Thank you.
Yeah.
Okay, welcome back from the break, everyone, and let's try some constraints.
Yep. So just for context for everybody, this morning we talked about the algorithms which you can use to solve planning and scheduling problems, right? We talked about the greedy algorithm, we talked about brute force, and we talked about the meta-heuristics. And now we're talking about how you define your constraints so that these algorithms know what you want them to do, what you want them to optimize, right? Now, let me first introduce you to a new use case. It's called employee rostering or shift rostering. And in this case, we need to assign shifts to employees. So for example, here we have a number of shifts. You can see here there's morning shifts from 6 a.m. till 2 p.m. That's the green ones. We have afternoon shifts from 2 p.m. till 10 p.m. And we have night shifts. Each of these shifts needs to be assigned to one of the employees. Here we have 4 employees with different skills. We have 2 nurses, we have a mechanic, and we have a designer. And we need to decide which of these shifts goes to which person, and of course that will also make sure that some people basically have free time, as you can see there, right, at certain days. So there's a number of constraints there, right? So one of the constraints is the 1 shift per day constraints, right? So that basically means every employee in this case can only have 1 shift per day, and that's a hard constraint. Of course, they can only do 1 shift at a specific time, but even further than that, they cannot do 2 shifts at the same day. There's also a skill requirement to be able to work in as a nurse. You actually have to have the nurse requirement, makes sense. And of course, in more realistic cases, this will be, for example, you have a hospital full of nurses, and some of them can have the maternity ward skill, right? And they can work in anywhere in the hospital or in the maternity ward, while other nurses cannot work in the maternity ward, as that requires an extra skill, right? And here you can also see we have one with the engineering skill or the mechanic skill, right? So this particular shift needs to be assigned to that employee, as he's the only one with that skill. There might also be things like contracts, employee contracts. So in this case, the designer has a contract that he cannot work shifts during the weekend. So obviously, we don't want to assign any shifts during the weekend there. Right?
Yes, exactly.
Yeah.
There should also be some soft constraints, right?
Yeah, indeed. Because these are just the things to make it feasible. If you respect these, you can actually put your plan in production, but that doesn't mean the employees will actually be happy or you will be delivering a good service or actually an economically good service also. So what you want to also take into account are these soft constraints. So one nice example is what they call forward rotation. And that means that between two shifts, you need at least 10 hours. Because if you would give an employee a shift at till 10 p.m. in the evening, so a late shift, and you would then give him him or her the next day a morning shift at 6 a.m. That basically means there's 8 hours between getting off work at 10 p.m. 10 p.m. and taking the morning shift at 6 a.m. And when you do that, that employee has 8 hours to go home, get some food, get some sleep, and come back. Obviously, that person will not have a full night's sleep, and that will be bad for that employee, but will also be bad for your hospital, of course, as they will not be as awake as they should be during their shift. So you want to avoid that, and sometimes that's a hard constraint, but in this particular implementation, it's deemed a soft constraint. You also have things like 5 consecutive shifts. That means that you could not have more than 5 shifts in a row. Then you need some time off. Like here, we could see a weekend time off. That means that they need 48 hours of rest. Now, that weekend doesn't have to fall on Saturday and Sunday. That can fall in the middle of the week. But every week or so, they need to have some more time than normal off, which counts as their mid-week weekend or something, right? And then the big one is the day off request. So what's the day off request? It basically means that the employee says, I would not like to work on that particular time. For example, for young employees, that might mean, or more vibrant older employees, that might mean that on a Friday evening they want to be free to go out, right, or to go to a party, and or on the Wednesday afternoon, that can mean that, for example, one of the nurses wants to take care of his or her grandchildren, right? So you want to respect those days, but you can't always deal with all of the day off requests. For example, Christmas, right?
Sometimes somebody's got to stay at work.
Yeah.
There's no way around that.
Yeah. Everybody wants to be free on Christmas, and you're going to have to force people to come to work anyway, right? So the day off requests are you want to do those as much as possible, but you can't always do them. By the way, you get this kind of problems with hospitals, with security guards, call centers, basically any type of employees that don't work 9 to 5 will see this. And we've done some benchmarks on a whole bunch of academic data sets as well. We've seen this in the real world with a whole bunch of hospitals and other kinds of organizations, security guard organizations, and so forth. And what you see is that typically, if you compare to the traditional algorithms, that's those greedy algorithms again, right? What you will see is that the meta-heuristics on top of that add what we call employee well-being. That's actually the combination of all of these soft constraints by about half, right?
That's nice.
Yeah, and most of the time that actually is the day off request. So 90% of that improvement is around day off request. So basically, by using these kinds of algorithms, you can say yes to your employees half of the time more that they get their off request. Now, this is you can imagine that this kind of use case is very different from a vehicle routing use case I showed earlier, right? This is not about reducing travel time or about saving a lot of money and ecologically. This is about making employees happier and providing a better service. And of course, there's some constraints that actually will affect the bottom line of the hospital. And of course, you can make these less or more important as you want. So let me give you a quick demo of employee scheduling. You can try this out yourself. This is open source code, Apache, so you can try this yourself. This is the Timefold Quick Starts repository. So if you go to the website and you clone this one, you can do the exact same thing as I'm doing right now. And I do have to click in the window. Here we go. And so if you go into the use cases directory, you'll see there's a whole bunch of use cases here. I'll just show you here on the left. Right, so and specifically now we'll look at the employee scheduling case, but as you can see, there's many more multiple variants of vehicle routing with capacity, with time windows and things like that. And the school one, timetabling, which we showed variation on earlier. So I'll now go into the employee scheduling one. Here we go, and I'll start that up. All right. This one, as you can see, is also using Quarkus. If you're looking into how can I use it with, for example, Kotlin and Java, and that's this one. If you want to use Spring Boot, that's this one. If you are missing any of the technologies, let us know, and we'll see if you can build some integration with that, some glue code with that, so you can use those two just out of the box. All right. So this one has started, and we are going to go here to take a look at it. Here we go. And I'm going to hit Control F5. That usually fixes it. Okay. So what we have here is we have a number of unassigned shifts, right? So the red squares are all unassigned shifts. So here we have an unassigned shift from 6 a.m. till 2 p.m. Here so from till 1400 hours to 2 in the afternoon. Here we have one from 2 in the afternoon to 10 in the evening, and all of these shifts need to be assigned to employees. You can also see that these shifts, it's a bit hard to see here with this color, but all of them actually have a skill requirement. So for example, this shift requires an anesthetics skill from the employee assigned to it. Let's take a look at our employees. Here we go. We have a number of employees. This is test data, of course. Amy King, Amy Smith, and so forth. And each of these have a number of skills. And you can see, for example, Amy King here has cardiology and anesthetics, so she will be able to actually do that one shift I just pointed out. And all of these employees have availability. Now, it's actually a bit more complex than just day off requests. There's actually 3 different states. You can have unavailable constraints. That's when they took PTO or something like that, right? Or they know they go into surgery or something like that. You know they're going to be away, off work. That's a hard constraint. And then there's undesired. Then they're basically asking, I don't want to take PTO for that, but I would love to go to that party of my friends. So can you give me a day off there or give me the evening off? So that's the orange ones. And then the green ones is the opposite, when they would love to work, right? But they would love to pick up skill shifts then. And so we have all that data available. Now what happens if we start solving, let's take a look back here, we start solving, you'll see that the TimeFold solver starts assigning these shifts. And as it goes on, you'll see that the score here on the top left improves better and better as it tries more and more combinations to
Oh, and now it actually got feasible.
Yes, it actually took a while. This is potentially a harder data set, I guess. You can see the soft score is still going up, right? So the hard score for a minute ago was -1 hard. Now it's 3,000. Now it's 0 hard, so it's feasible schedule. And so no employee has 2 shifts on the same day. There's always 10 hours between 2 shifts. All of those stuff we talked about earlier, as well as there's a number of soft constraints that are playing in. You can see the soft score is positive. Why is it positive? Because every time one of those things is green, and so let me just show that a bit clearer here. Every time one of those things is happening during the hours, and it's actually the amount of hours that is within that thing, we actually win points. And of course, the orange ones, that's where we lose points, right? So just to give you so we deal with the soft and the hard constraints together, and the soft constraints are weighted both on undesired shifts as well as desired shifts. Now you might want to, you can play with the weights and you can say, I really don't want undesired shifts and I don't care that much about the desired shift. We could do that and we could change the weights and you would get a different solution with a different accents on that, right? As you can see, we can solve as long as we want. We've terminated solving, but we could solve this for, if we are ever solving this during the night, we could solve this for an hour. If somebody's actually watching this, if they say, I need to schedule and publish it within 30 seconds, then we solve it for 30 seconds, whatever is the time we have available, right? So let's talk again, let's do a refresher on that scoring thing. So here we have those 8 shifts that we need to assign, right? 2 early shifts on Monday, 1 late shift on Monday, and then a whole bunch of other shifts. We have 3 employees. The first employee here, this nurse, wants a day off on Wednesday, and the mechanic also wants to have a day off on Wednesday, right?
Yeah.
Okay, so let's see how that would solve, right? So let's say the solver generates this solution, and we can see some of the hard constraints are broken, right? So you can see that there's a skill missing on the early shift assignment because we need a mechanic for this particular shift and we assigned a nurse. Obviously not a good idea. And here we are assigning 2 shifts on the same day to a person and that's not allowed either for legal reasons.
Yes.
Right? So how do we formalize that? Well, we said we calculate a score based upon that. Well, this is the score. So we basically, for each of the hard constraints broken, we lose 1 hard point. And it could be more than 1 hard, but 1 hard is enough. And we would then see that the score ends up as -2 hard, and no soft constraints are broken, so 0 soft. Right? Here's another solution. In this solution, we have we have the day off request denied, right, for the mechanic, but we also have twice where the employees only have 8 hours between 2 shifts instead of 10, right? So when we start scoring this, you'll see, of course, there's no hard constraints broken, so the hard score will be 0 hard, as you see here. But the soft score will be, in this case, it's -5, because we lose 1 point for the day off request. But we actually use 2 points per this case because it's per hour that it counts. And there's only 8 hours between. We need 10 hours, so that's why we would actually lose 2 soft points. We can actually weight that. And of course, we can weight the day off request higher, but in this case, we've chosen to weight it like this. Anyway, so we get this score. Now, between those 2 solutions, which ones do you think is better?
Well, this is easy because the first one actually breaks hard constraints, so we cannot use it. So we have to use the second one.
Yeah. Very easy. So we look at the hard score. If the hard score is a higher number, we pick the one with less hard score, with a better hard score, right?
Yes.
Now there's a third solution here. In this one, we only have the day off request denied, as you can see, and there's no other soft constraints broken, no hard constraint broken whatsoever. So the score just becomes 0 hard -1 soft. Now, given these 3 solutions, which do you think is best? What do you think, Lucas?
The last one, unless I'm the poor mechanic guy.
Yeah, of course. But so this is the best solution out of these 3, right? So this is basically what we now need to implement in our constraints. Now, I'm going to go a little bit deeper now, but a little bit go into more fun stuff. It's about one thing you have to understand is how do we calculate the score? How do we calculate the score and are able to scale, right? Now, earlier we shown you the easy score calculator where we had 2 for loops going through all of the things, but let me show you what happens when we actually use that in production. So the first time we need to calculate the score for this particular solution, we just have to go through each of the shifts, right? And we have to check if, in this particular case, we'll just check the required skill constraint, just as an example. You'll see that it's fine for this shift because it needs a nurse and has a nurse, fine for this shift, needs a nurse, has a nurse, and so on. But for these 2 shifts, we need a mechanic, and clearly it's assigned to a nurse, so that's a broken hard constraint, right? And so we sum up all of those numbers. You can you can already see the code where we for loop through all of these shifts, right? And we sum all of these numbers up, and we get -2 hard, which is very similar to what we did with the easy score calculator earlier this morning. Now, what then these algorithms do, this is both for the greedy as well as for the meta-heuristic, and to some degree also for the brute force, is that they start changing things. So if they take, for example, that particular shift and move it from this employee from the second employee to the third employee, as you can see, right? And so what happens then is we need to calculate the score again. Now we can calculate the score the exact same way, right? And what we do is we just go through all of the shifts again, right? And we sum up all of that number, and we have then the score of -1 hard. And that is the correct score. This is correct. But there's a problem with it. Why? We want to do this, well, we do this 10,000 times per second.
Often even more.
Yeah. Well, the faster we do it, we want to do it 100 times per second. And sometimes
million times per second we want to do it.
Yeah. So the faster we do this, the more we calculate scores we can calculate per second, the better our algorithms work. Right? This is like the thing that drags down the speed of our algorithms. And it's a very complex calculation because often it involves multiple shifts, right? For example, shift conflicts, or maybe 3 or 4 shifts. So it can be quite complex calculations to calculate these constraints. So what if we find a better way to do it? Anybody can see that? Well, what we can do is what's called doing deltas or incremental calculation. So we know from the previous calculation that the total score was -2 hard. So what if we start from -2 hard and just check what the delta is, the difference is in the changes we've made? Because we know we've only changed this part, right? This particular shift. So what we can actually do is ignore all of the other shifts for this particular constraint, for the required skill constraint, and we can just say, okay, it used to be here, now it's no longer. We used to lose 1 hard point there. Let's just undo that that losing of 1 hard point. So let's do +1 hard point, right? And then at the new location, apparently we lose 0 hard points, right? So that gives us 0. And then we just take the old score, the -2 we got from over here, right? And then we add that delta, which means +1 because of the undo, and -1 for the new place it is, and we get this required score of -1. And of course, this score is exactly the same as the last score. If it's not, we have something we have a name for already.
Yeah, it's called a score corruption, and you don't want to see that.
Yeah. So so writing deltas is extremely hard, right? And
it involves caching. It involves hash maps. You need to make sure that once you remove something from somewhere, you put it somewhere else. So it's hard. You don't want to do that yourself.
Yep. But you do want it, because your algorithms will go a lot faster. In fact, for those who are familiar with big O notations, this is basically getting you going from big O n to 1, or for big N O squared to n, depending on which constraint we're talking about. So it is not just, so if your data set is like 1,000 lessons or 1,000 shifts in this case, it's typically makes you 500 times faster. That's a lot, right? Not 500%, 500 times faster, like 50,000%, right? So not doing this is really not an option when you want to scale, right? So can we have our cake and eat it too?
I think we can.
So for the record, having our cake means I want this, but I don't want to implement it.
Yes. So you can actually get incremental score calculation with all its benefits without writing incremental score calculation. And we're going to show you how you can do that with Timefold Solver. But first, we need to talk a little bit about how you define the problem in Timefold. I almost set up the planner there. It's Timefold. So we have something called the planning solution, which contains all of your data. That's the part you give us from a database or from a JSON. We deserialize that into a Java class, and it's got 2 particularly important parts. It's got the entity collection property and the fact collection property. The entities, those are going to be our shifts. Those are the things that change. And the employees are going to be the things that we assign to the shifts. So those don't change, and we call those problem facts. There's one more thing on the planning solution, that's the score. And you've already seen what the score is, so let's not get further into that.
Yeah, now, Lucas, this seems like a lot of boilerplate. We didn't talk about that earlier, these annotations. Is it always the same between the problems, or is it very unique?
Right. So the annotations, they're the same for every problem. Yeah. But obviously, your domain models will differ. If you're doing vehicle routing, you're going to have visits and vehicles, where in our case, we have shifts and employees. Yeah. But no matter what particular domain model you have, you're still going to have the planning solution annotation, the problem fact collection property, the planning entity collection property, and the planning score. And we kind of have something on our backlog to make most of this just go away.
Yeah, but that's very different from the planning entity and planning variable showed earlier. That is that's something we cannot just know.
Yes.
That's you defining what we can change in your model, right?
Yes, exactly.
Okay.
So now let's take a look at how we actually give you the benefits of incremental calculation without having you to write incremental calculation yourself. We have something called the Constraint Streams API, which is very similar to the Java streams, and also it's got a lot of familiarity with SQL, which I'm assuming you've seen before. And let's talk about how it looks. So every constraint stream starts with the call for each. In our case, it's for each shift class, which means we're going to get something we're calling uniconstraint stream, which contains all of our shifts. Those shifts are the ones that are being loaded from the entity collection property. And in our sample data set, we have 4 shifts in there. We have Anne on February the 1st, Bev on February the 2nd, Bev on February the 3rd, and Anne on February the 4th. So the uniconstraint stream contains 4 entries, which I just named. Next thing we might want to do is we might want to call a filter, which is going to take the uniconstraint stream with the 4 entities, with the four elements, and it's going to give us a smaller uniconstraint stream at the output. In this case, we say by providing a lambda up there that we want all the shifts where the employee is Anne. So that's what the filter does. It takes the 4 shifts as an input, and it filters the stream to only contain the ones where the employee is Anne.
Yeah. Why would you want to do that? Why would you want to filter out Anne except of the other employees?
So maybe Anne is a contractor. Maybe she's very expensive.
Yeah.
Maybe we have our own employees that we want to use first.
Yeah.
So that's why we may want to filter out Anne specifically.
Okay.
The important part is that filter takes the stream on the input and it removes some parts of it on the output. After which we can create our constraint, and we say penalize by 1 soft. So each Anne instance is going to have a penalty of -1 soft. And the constraint is called don't assign Anne. It's very simple.
So why is it soft?
Well, it is soft because we may not need Anne, or we do need Anne.
Yeah.
It depends. Like, if we can fill our roster with all the other employees, we don't need Anne.
Yeah.
But if we cannot, then yes, we are going to pay some penalty for that, but the roster, the solution will still be feasible.
Yeah.
So for each N in the filtered constraint stream, we have a penalty of -1 soft, and that sums up to -2 soft. As you can see, instead of processing 4 elements, we have now only processed 2, and then the resulting score of -2 soft is stored directly in your solution, and it's ready to be sent back to you, to your database, or over the via JSON, or anything like that. We've already seen the filter, so this is it. The filter actually accepts any kind of a Java lambda. This is normal Java code, so you can write any code in there you like. Maybe don't do much computation there, but you can if you want to.
Can I put a breakpoint in there?
Maybe you shouldn't.
I can.
Oh, you mean like a debugging breakpoint?
Yeah,
I thought like a break. So like a break command. Yeah. Let's
No. I mean like a breakpoint.
Yeah, sure.
Show
of
me
course,
what's
you can put there a
happening.
debugging breakpoint, and the debugger will run this as usual because this is a normal Java code like any other Java code.
Okay.
We have already talked about what the filter does, so let's not reiterate that. We have the penalize at the end. But
So penalize means negative constraint, right?
penalize means negative constraints, and we can do reward for positive constraints.
Okay.
Here, though, we see that we operate on a uniconstraint stream, which only has a shift, but that's not the only thing we can do. We can also operate on something which we call a by constraint stream, which carries multiple items in each element. So in this case, it's got shifts and day off requests. So this is a full Cartesian product, or rather a partial Cartesian product, of all of our shifts and all of our day off requests. As you can see, we've got the shifts from Anne on February the 1st, and 2 shifts from Bev on February the 2nd and 3rd. And we've got 3 day off requests, which are the same day off request. Bev doesn't want to work on February the 3rd. So why do we have them like this? Like, 2 of these 3 items make no sense because we only want to match the shift with Bev on February the 3rd with the day off request on February the 3rd. So we use a filter. We use a filter which this time accepts 2 arguments. It's a by predicate, and it's a by predicate which makes sure that the shift date is the same as the date of the day off request, and that the employee of the shift is the same as the employee of the day off request. So from the 3 items on the input, our by constraint stream now only has 1. And we can actually introduce a penalty for that because we have managed to schedule Bev on a day where Bev would prefer not to work. This ideally would be a soft constraint.
Yeah. So
Now,
why do we do all of this? Why not just write the for loops in the easy scale calculator?
yes, we do all of this because we care a lot about large data sets. We care a lot about large data sets, and that means that we're going to have, if we just keep iterating over and over and over those data sets, we're going to be doing a lot of work, and that's going to be slowing the solver down, and that's going to result in us getting you worse solutions. So we want to reduce the iteration to a bare minimum, and let's take a look at how we do that. Once again, we've got the for each, we've got the filter, which filters out anyone but n. We've got the penalty. You've seen all of that. Now imagine what happens if we actually have not 5 shifts, but 1,000 shifts. The way the solver works is it's doing these little local moves like you've already seen. And these little local moves, they will typically switch a shift from one person to another person. So in this case, they're going to switch Bev and Anne from February the 3rd to February the 4th and vice versa. So that's a change of only 2 shifts out of 1,000. So what we need to do, that's our job, that's the job of constraint streams, is we need to only recalculate the score for the 2 shifts that changed and leave the other 998 completely untouched. Don't iterate them, never visit them. That's how we get the performance. So what we need to do is we need to actually remove Bev on February the 3rd from the solution. We need to add Anne on February the 4th into the solution. But because we still have the same, because we still have Anne there once, we still have the same score. But this time we actually managed to get to the same score by only processing 0.2% of the data set. And that means we are 500 times faster.
Yeah, in this case, yeah, something
500
like that.
times faster than if we just had to iterate over the entire thing.
Yeah, and it depends on your number of shifts, right? If you have 500, if you have 100 shifts, it would not be that fast. But you have 10,000 shifts, you would really want this because it would be 5,000 times faster in theory, right?
Yeah. So maybe we don't want to deal with 10,000 shifts, but there are problems which are truly massive, where you've got tens of thousands of entities, like for example vaccinations in countries and stuff like that.
Yeah.
So that's where you really, really need incremental calculation, and you really need this to happen.
Yeah, in vaccination actually you have hundreds of thousands.
Hundreds of thousands, yes.
Just for the fun of it, go for it.
Now, we've already seen that we have a unit constraint stream and a by constraint stream, but we haven't yet shown you how you can get to a by constraint stream. So we're going to introduce a concept, which if you're familiar with SQL, you already know that concept. We're going to be calling it a join. So let's create the by constraint stream we've seen before. We've got the for each on shifts. We've got the for each on day off requests. And we want to join them together using the join call in the constraint streams API. What you get is a full Cartesian product of all the shifts and all the day off requests. This in turn means that the by constraint stream is going to contain 8 elements for all the shifts and all the day offs multiplied.
Seems like a lot, right?
That's a lot, yes. It's a Cartesian product. Now we can have the filter you've already seen, because we only care about 1 out of those 8. So you can ask a question, why did we create the other 7? Haven't we just wasted a lot of cycles? Haven't we just wasted a lot of memory creating all of those objects if we just need 1?
Yeah, and more importantly, you now have 4 shifts to day off requests. What if you have 400 shifts and 200 day off requests?
Yeah,
that's
of course the first Cartesian product grows very, very quickly. And we've already seen that kind of with the brute force. That's part of why brute force also didn't work.
Yeah. Now, incremental scoring cannot fix this for us, right?
No, but there's other technologies that can solve this, other principles. as you can see, we have the wasteful Cartesian product because we're not actually doing any indexing. So you're not going to want to use join like that. You want to use join like that. We call this a joiner, and this is a declarative way of how you tell us which things should be the same, which things should enter the hash maps, which things should enter the indexes, which things should be cached. And essentially, what you see here is that we have a join where we say that the shift date needs to be the same as the day of date, and the shift employee needs to be the same as the day of employee. And once we understand your query like that, we can actually give you what you want. We can give you a fully indexed join and the by constraint stream. Because of indexing and because of hashing, we can actually get you much faster because we don't need to iterate over all of those things.
Yeah, and we don't need to create those instances in memory. So if you look at this with Java Flight Recorder and stuff like that, the number of allocations doesn't blow up.
Yes.
Yeah, I like that.
Yes, definitely.
So why not use this all the time? Why what are the limitations with this?
Well, obviously indexes cost memory, right? You need to build them, so they're going to be heavy.
Yeah. And I imagine also you can't just filter, right? What you see there is on the left side, we say the shift get date needs to be the same as the day of request, the get day of request get date, right? So we actually need to match both of these fields. And in a normal by predicate, we can actually do more elaborate stuff with that, right? So it has some limitations. Can we combine them? Can we first do a join on some equal stuff and then still have a little bit too many results and
sure.
narrow those down with a filter?
So all the operations we are showing here are actually composable. So you can join. So you can do a for each filter, then a join. You can do a filter, a join. You can do a for each join and then a filter. And there's a whole bunch of other operations we're going to show you later, and they are all fully composable. So yes, you can filter before a join, after a join. You can filter anytime you want, but preferably you filter after a join because filters are not as smart. Filters are not indexed.
Yeah.
Okay, let's just finish this slide. So we've already seen we've got the indexing and hashing of the date and the employee, which means we scale better because we don't need to maintain the Cartesian products.
So this is basically like an SQL aware class, or like in
Yes, exactly. But it has the extra sort of ability that we can actually put any kind of lambda in there. So you can have calculations, you can call your own functions, stuff like that, if you need to.
Okay, nice.
So, I want to introduce you to another concept, and this is going to be special because this is, we call it group by, and this is a concept which is actually capable of transforming data in your stream. So what we've seen so far is filter that was removing stuff from the stream. We've seen join that was putting things together. But now we actually have group by, which can produce something entirely different as an output. It's a mutator, it's a transformation if you want. How does it work? We make the group by call, and let's say we want to group by the employee of the shift. What happens if we do it like this is it creates a brand new constraint stream which only contains the employees now. So you've got only two items in the constraint stream because you only have 2 employees in those shifts. You only have Anne and Bev. Now this on its own is not too useful, but we can also do something else. We can add something to the group by which we call a constraint collector. And if we say use the constraint collector count, we can count the number of items in those groups. So you see that once applied, we get a by constraint stream of employee and of integer, and we see that from the original constraint stream, we had 1 N and 3 Bevs. So this is how you can create new things from pure data, new things that have not existed before and which you do not have anywhere in your solution. This is how you can get brand new data, how you can transform data into new, not previously seen things.
Yeah, so the count I might be able to use for things like I don't want more than 5 stops in a particular trip or something like that. Can I do anything else beside count?
Yeah, we have a whole library of constraint collectors. Obviously, we have the normal stuff like sum. We have the averages, but we also can do really smart things with those constraint collectors. Like, for example, we can get you a list of all shifts that come right after another.
Sequential shifts.
Sequential shifts.
Oh,
We call them consecutive shifts.
Yeah.
So this is very powerful, and actually you can implement your own constraint collectors because every constraint collector is an interface. It's called constraint collector. And when you implement it, you can have any functionality you want. So the yellow part right there, it doesn't need to be an integer. It could be a collection. It could be any random object. The important part is you're taking stuff from the left, from the uniconstraint stream, and you're putting it in a group. And on the entire group, you can apply any sort of reducing operation.
Yeah, okay. And after this group by, I can then join it again with others.
Yeah, you can
if
again
want.
join and filter and do all the stuff. Or you can group again if you like.
Yeah. By the way, you showed by constraint streams, but can I like do more if I need 3 objects? Like give me 3 shifts on the same day or something like that?
Yeah, if you call join again on a by constraint stream, you're going to get a tri constraint stream. If you call join once more, you're going to get a quad constraint stream. And that's where we end.
Yeah.
We don't go higher than 4.
But if you do have cases where you go higher than 4, there's ways to do with that, where you can tag them into a new object and you can continue.
Yes, yeah.
But we see very little people need that, especially with this group by.
Yeah, the constraints we're seeing so far barely ever go above tri constraint stream.
Yeah.
For, quad constraint streams are very rare.
Yeah.
So the last thing I want to show you today from constraint streams is the ifExist call. And that actually is there for you to be able to only pass elements to subsequent streams if something else is true. So let's take a look at, for example, our shifts. We've seen that before. And let's, for whatever reason, say that each of those employees can have a pet. So Bev has a dog, and Karl has a dog, and Karl has a cat, and Karl has a bird. I wouldn't want to live in Karl's place, but I made myself laugh. Sorry? So now we want to propagate only those kinds of shifts, for whatever reason, where the employee has a pet. So how do we do that? We call the ifExists call. There's a familiar thing you can see there. This is the equal joiner. You know that from the join. So that should tell you that this operation is also indexed, hash maps, everything. And you get a new constraint stream, which is only filled with those items where those employees actually have a pet. Notice that the pet doesn't actually show up anywhere in the constraint stream. That was just a precondition we needed to move the shift from one stream to another. So this is a combination of a filter and a join. But because it doesn't actually create the Cartesian product in any way, it can be actually faster than a join is in some cases.
Yeah. Now, what if I want to do the opposite? What if I want to find all of the shifts for people who don't have pets?
Yeah, it's very easy. Instead, you just have to replace ifExists with ifNotExists, and you're done.
Okay. And I also see we use an equal there. What kind of other joiners do we have?
Oh yeah, we have the ones you would typically expect. We have less than, greater than, less than equal, greater than equal.
Yeah.
The standard stuff.
Yeah, makes sense.
Okay, moving on. As you can see, the number of matching elements in the second stream has no influence. It just makes sure that the second stream only contains the items where the pets are actually matched to the employees.
Yeah, why not just use Java streams? I mean, they have collectors too. They have a lot of this stuff, right?
Right. So the reason there are actually two reasons why you want to use, for our purposes, constraint streams and not just pure Java streams. The first reason is, as we've explained, the incrementality. We are going to process those items incrementally, and then hopefully we are going to remove much of the iteration that would have otherwise been here. And also, the constraint streams are scoring specific, so we can terminate with stuff like penalize, with stuff like reward. We can also support score explanations. So we can tell you why your score looks the way it looks. We can tell you which hard constraints were broken and by which entity, for example. And none of that we could get if we just used the Java Streams API. The Java Streams API is very nice, but not for this purpose.
Yeah, but we were very heavily inspired by that. Right?
Oh yeah,
yeah.
Hopefully it shows.
Yeah.
I think it's time for a demo.
Yeah, time for a demo. So we showed the school timetabling case earlier, right? And let's take a look how it looks like to write those constraints in constraint streams. So right here, we still have the shift scheduling running. I'm going to go to the school timetabling one. Here we go. I'll fire that up. And I'll also, let's go into the code here, school timetabling. So as you can see, you can run this with Maven or with Gradle, whatever you prefer. And there is in here a constraint provider already, which is fully implemented. So I'm going to actually just throw away all of that code so we can have a look at it. Here we go, and delete it. Maybe, yep. And we also have tests for this. And so obviously those tests won't work anymore. So we're going to do this is the test, by the way. Every single constraint is nicely tested with a unit test. This is what you should be doing. What you should not be doing is deleting the test like I'm going to do right now. So it doesn't bother me anymore, all right? Live a little, right? So let's take a look. We need to implement here something, and that's the define constraints function. I'm just going to have that return an empty array. Later we will fill in some of these constraints. So now we have no constraints for school timetabling. We've started up, as you can see here at the bottom. So we're going to go to this. We're going to refresh. All right, maybe just for certainty, control refresh. I've become paranoid today. And let's take a look what happens if we solve this problem with no constraints. What will the solver, what will Timeful Solver do for us? Press the solve button, and it puts everything, all of the lessons in room A at 8:30. And the score is perfect, right? Again, there are no constraints. So now we need to add some constraints, right? So let's go to the implementation here. You can see it's running at the bottom. I'll just stop it for a second. Doesn't really matter. It's a lot of output there. Let's actually reduce the output a bit. So if you go here into resources, application, here, let's put that on info, all right, and then we'll have less output in a minute. And so I'm going to add a constraint here, the room conflict constraint. For the record, we had to turn on off Copilot because otherwise it just generates it from us because it learned from exactly these examples. So it's nicely turned off. Here we go. So we're going to write a room conflict constraint. So how do we write a room conflict constraint, right? We had those things, like we had joins, we had filters, we had that kind of stuff, right? So let's start from the constraint factory. Let's say for each of the lessons, right? And in the end, we'll do a panelize. So I'll write that already, all right? So every time we have two lessons that are in the same room at the same time, we have a problem. Obviously, we need two lessons. Now we only have a unique constraint of one lesson, so we're going to need to do a join with another lesson. All right. Now we have, as you can see, a by constraint stream of lesson, right? And and we need to say only the ones where we have the same room and the same time slot. Now we could do that in two different ways. I'm going to start with the filter first, which is not the way you should be doing it, but it does work. So we do a lesson 1 here, lesson 2, and we say basically if lesson, this is lesson 1 apparently. Let me do that right. if we do lesson 1 dot get time slot, and that is equal to lesson 2 get time slot, then now they're being done at the same time. But obviously, we also need to make sure that they're in the same room. So lesson 1 get room equals lesson 2 get room, right? Then we have a problem. So then we're going to penalize by hard soft score, So hard soft score of hard 1, right? And we need to return this as a constraint, and we need to give that a name. We're going to call that the room conflict. So why do we need to give it a name? That's mostly for good practice for the score explanations later. Every constraint needs to have a unique name, so it can actually tell you when it has a certain score. Why the score is -5 hard? Well, it's because it broke the room conflict constraint, or it broke the teacher conflict constraint, right? Okay, let's try this out. Let's run this. So we go here, we click F5, all right. Oh, F5 now is the right button. We solve this, and let's take a look. This looks good, right? No room conflict constraints. The score shows -20 hard. I'll talk about that in a minute. But obviously, we have mistakes in the teachers, as you can see here, because we completely don't have this constraint yet, and probably in the students group. They actually went fine. This is more luck than anything else. But obviously, this doesn't take into account the other constraints yet. What is the -20 hard here? Well, the -20 hard is because it combines every lesson with every lesson, not every other lesson with every lesson. So it combines lesson A with lesson A, right? And obviously, when you have twice the same lesson, then they have the same stamp, so it's the same room, and you actually lose those points. So what we actually do want to do is, on top of that, we should probably do that in the same filter, but you'll see in a minute that why I want to do that in the second filter is what I'm going to do is make sure that these lessons are actually different, right? So lesson 1 is different from lesson 2. Okay, and then if we do this, just to show it works, right? Here we go, we solve this, you'll see that the score here on the top actually now is nicely 0 hard, right? Okay, Luka's just spoken earlier a moment ago that this actually creates a Cartesian product, so once you start scaling, this will not be as nice. It will be incremental already, so you will scale a lot better than the for each approach, but you actually want to make use of indexes here. So what we're going to do is we're going to say equal, and this comes from the joiners basically. And we say, okay, we want to equal that they have the same time slot. And we also want to make sure they have the same room. So instead of writing these here, I'll just put these in, comment these out. You can see now we've written the exact same thing that I want to join with another lesson where both of the lessons have the same time slot and the same room. You can actually give it 2 parameters in case you want to pick something else from both sides. But if it's actually the same class, you can actually use this trick, which is even less code. So let's try it out again. We refresh and we solve, and we can see it still works nicely. And we have 0 hard broken, but we still have that problem with the teachers, right? So let's add a teacher conflict constraint. So here we go. Oh. Teacher conflict, right? I'll make the alienation, the indentation nice, and let's generate that method here. So now I'm going to use. We have actually a construct. It's so often we see this where you want to say, I want to select 2 lessons, 2 entities, right? 2 things that are the same thing and that are different. That's something we see so very much often that we added some syntactic sugar for that. And it's called for each unique pair. So for each unique pair basically means give me all of the lessons where give me every combination, every pair of lessons where the first lesson is different from the second lesson. So don't select AA, only select AB, right? And also where it's unique. So if you select AB, don't select BA, right? It's quite useful. What we're now going to do is for this unique pair, we can add some joiners in there. So we can say, okay, I want to have an equal lesson get time slot we said earlier, right? So now we have two unique, two lessons that have the same time slot, and we want to do the teacher conflict, so we better look at the teacher too. So you want to say lesson get teacher needs to be also the same, right? And of course, if this happens, we want to have a penalize and we want to have as constraint, right? So we want to have a penalize it on hard soft score of hard, like the previous one. We lose 1 hard point when this happens, and we want this as a constraint called teacher conflict. Okay, and we've so let's go through this again. Let's put the indentation fine. So we have for each pair we select 2 lessons, unique combination. If they have the same time slot, if they have the same teacher, then we're going to hit time slot solver on the head. Don't do that. Let's see what happens if you tell them not to do that. We still have the other constraint, the room conflict constraint, active. And you can see both of these constraints are nicely isolated and separate methods from each other, which will also appreciate once you start unit testing this, because you can unit test them separately without caring about the others. And so the others can change, and your unit tests on this constraint won't be broken. And that's really a really big benefit towards maintenance work. Anyway. We solved it here. Let's take a look, right? So we have the rooms look good, the teachers look good, right? Or at least it's a feasible solution. And let's take a look at the student groups. Oh, yeah, that's where we have a problem, right? So just to speed things up a bit, let's copy paste this constraint. So I'm going to just duplicate this teacher constraint, right? This teacher conflict constraint. I'm just going to say this is a student group constraint, and I'm going to change the time slot so that it needs to be the same time slot but the same student group, right? So now if you have two lessons with the same student group, help me a bit here, yes, this one. So now if you have 2 lessons with the same time slot, the same student group, we're going to break this, all right, and we're going to add this into our constraints that we want to have active. And we have a whole bunch of stuff on top of this, by the way, if you want to have your data set determine if a constraint is active or not. But this is just the hard-coded way, which works great for demos. And let's take a look what happens. Let's do a 5. Oh. So one of the things we pride ourselves about is that we have very good error messages in time fault solver. Anybody want to, let me zoom in a bit. Anybody want to take a care what actually happened? There are multiple constraints with the same ID, and then there's the namespace of the constraint and the teacher conflict. So I clearly made a mistake here. I forgot when we went to the I forgot in the student group constraint to actually change the constraint name. So let's try that out. Student. It's not going to check me on spelling mistakes, so maybe. But anyway, and let's filter this, bring it back to normal speed. You can see if we solve it now, that it will actually take into account all of the constraints. So here we have the room, looks good. You have the teachers. Looks good, no, it's feasible, and no 2 teacher has to be at 2 places at the same time, and our student groups. Let's kick it up a notch, right? Because if you look at the teacher constraint, what do you see here? Do you think this is a good schedule for the teachers? Imagine you're a teacher. Imagine you're one of these 5 teachers here, right? Imagine you're Marie Curie or so forth, and they tell you this is your schedule. Let's take a look at Marie Curie here. She has 2 talks on Monday morning, then she has like a long time between 10:30 and 1:30 where she doesn't have any classes, then she has 2 talks, and then she can show up just for the fun of it Tuesday evening, right? So this is a feasible schedule. This is what they often do to teachers in schools, right? But it's not something we want to do to them, right? It's just a bit hard to take that into account. So let's see if we can actually add a constraint that solves this, that makes this better, right? Now, first of all, is it a hard constraint? No, because if it would be a hard constraint, there's probably, you cannot make this perfect. We know this, right? But you can make it better, right? And that's clearly a sign that we need a soft constraint for this, because we first want to deal with all of the hard constraints, like people having to be at 2 places at the same time. So let's go back here and let's add a constraint. I'm going to call it teachers happy. Right? Probably need to find a better name, but anyway, here we go, and I'll generate it. Now, how would that constraint look like, right? So we return, how would that look like? What do we have to select, right? So there's a few ways to implement this, and but what I'm going to do specifically now is I'm going to look at all of the lessons for a specific teacher, where the next I'm going to reward good behavior. And what is good behavior in our schedule? So I'm going to write a positive constraint. This is good behavior, what you see here on the left. Lessons back to back, they love that. So I'm going to reward that, right? Instead of penalizing things. Let's be positive for a change. So we are actually going to say, okay, give me 2 unique lessons, right? And if they're back to back for the same teachers, then we're happy. So in there, we're going to say, we're going to say, okay, we want the same teacher. So now we have 2 unique pair of lessons. Let me write the other stuff first, so the help goes out of the way a bit. All right. So we have now 2 lessons that have the same teacher. And now we also want to make sure that they're on the same day, because as you can see here, we have Mondays and Tuesdays. So only lessons on the same day are good, ideal. We want to make sure those 2 lessons are on the same day. Let's do that. So let's say here, give me the lesson get day of week. Get day of week is, of course, okay, no, it's not on the lesson, it's on the time slot. So what we can do here is actually we can add in a full lambda here. We can say, give me the time slot, right? And get me the day of week. Notice that the time slot is not NULL, otherwise you would get a null pointer exception. So by default, the for each will actually filter out all of the ones with null time slots. If you do need them, you can get that by asking for each unfiltered. But by default, it will only give you lessons that are actually assigned to a time slot and to a room, which is typically what you want. So now I actually have 2 lessons on the same day, right? And let's just run that for a second. So here we go of hard soft constraint. I'll just do of soft 1, all right? And I'm going to call this teachers happy, all right? So let's run that. They're not back to back yet. So what I've done here is basically if we have a teacher that has 2 lessons on the same day, then we're going to reward that. And so we're going to try to get all of the lessons to happen on the same day, right, for the teachers. So no hard constraints broken. You can see the soft score here. Right? Oh, I used penalize. So I actually, let's see what this run out. This is not part of the demo normally. So it did the opposite. It nicely spread everything out across Monday and Tuesday. So this has happened before, right? And then we get interesting questions like, why is it doing the exact opposite of what we wanted to do? It's because that was penalize. If we make this a reward, I think this is going to go a lot better for this demo. Here we go. So now you can see the score becomes positive, yeah, all right. And and again, all of the other constraints are met, and then you can actually see here that it is really packing them more in the same day, but it really doesn't care about the gaps, right? Okay. Now you do see that for Darwin here, he does have 2 different days, and that's simply because of the other hard constraints. It's sometimes difficult to explain, but basically, the room conflict constraints, the teacher conflict constraints, and so forth, they all play into this solution. And to be able to satisfy those which are harder, which are more important, Darwin doesn't. We don't get to have Darwin 2 lessons on the same day, right? Now let's see if we can actually make it back to back. So what we can then do is we can do that filter in there. So we can do filter lesson 1, lesson 2. I'll just keep it simple now and just say if they're back to back. Here we go. lesson 1, get end time. Again, so get time slot, get end time, get end time. If that is equal to, it's not really helping with, but anyway. Lesson 2 here, get time slot, get start time, right? So if the end time of the previous lesson is the same as the start time of the next one, then we want to reward this. Now in a real world context, we actually want to do a duration check here, check if there's is less than 30 minutes between, because of breaks. You will have typically a break around 10 o'clock. So if you just look at the end and the start time, that will not be enough. Around lunches, you might probably want to do that too, because people don't consider lunch hour waste of time. Actually, they often like it. Well, everybody likes it almost, right? Almost everybody likes it. And of course, you could have teachers who don't like long lunches and teachers who do like long lunches, and you can play that along based upon the teacher you select, but that's a different, it's a far more elaborate constraint. Anyway, let's take a look at what we have here. Oh, it looks weird. That didn't do what it's supposed to do. What did I do? I checked if the lesson 1 end time. So these are, of course, I need to use equals here. Java 101. All right, because those are Java time instances. So obviously I need to use equals there. Here we go. Live demos are fun. So what do we get? We have 8 soft here, right? You can see it really has troubles with the lunch breaks, right? So here's a lunch break at 10:30. Here's the day break at 10:30. So there's very little it can do sometimes to deal around with that, but it is more compact than the first schedule we have. Now we could actually combine both of the hard constraints. Look, it's actually finding better solutions. It's hard for it to do that. But you can see it is really getting those back-to-back lessons far more than we have in the original implementation. Although I would prefer or maybe combining them with the soft constraints to have them on the same day, right? Here we go. And if we solve it longer, we'll probably get better solutions, of course. So let's get back to the slides. So constraint streams. Constraint streams is a streams-like API. It's fast, it's scalable because of the incremental score calculation that Lucas also showed, and the index joint that Luka showed, and because of and it is custom code friendly, right? And that's something you will definitely see if you look at other solvers, is that the timefold solver allows you to write your constraints in Java code, right? You might need to use these streams, or you can use the easy score calculator if you want something more simple and you don't need to scale that much. But you can implement your constraints in normal Java code. If you look at other solvers, they will typically ask you to write mathematical equations. And I can tell you it can be very, very hard to translate some of the business requirements into mathematical equations, especially if you have to deal with fairness or load balancing. It's hard, and that's something we just support out of the box, basically. Okay. Let's talk about responding to change, because up to this point, we first talked about the algorithms. How can you find a good algorithm to find the good solution? The next part we talked about was constraints. How do you tell the solver to find what you're looking for? How do you tell it what you want so it actually finds what you're looking for, a good schedule that you love, right? Now, the last big thing that we see that you need to know about, and this is something that people only think about much later down the line, is how do you respond to change? How does it work in the real world? How does your scheduling fit into your operations, basically? And there's an interesting quote from Winston Churchill around this. He said the following thing: plans are of little importance. Okay, so thank you for listening for 2 hours. Plans are of little importance, but planning is essential, right? And it's a good quote to think about this. You will make a plan. It will not be executed exactly the way you make it. If you don't make a plan, that's a much worse situation. So planning is essential. Making these plans for the field to execute is very important, because that will give them a much better experience for everybody. But they're not going to go exactly according to plan. Mike Tyson had another approach on this. He basically said everybody has a plan until they get punched in the mouth, which is also an interesting approach. So what kind of planning disruptions do we typically face, right? So this could be local disruptions, so limited to one department or region, or it could also be global disruptions, like impacted across the board. Give you an idea of a local disruption: somebody who calls in sick, right? This could actually be today. Somebody who says like, I won't be there in 2 days because I won't pick up my shift in 2 days, even though you planned me to pick up that shift in 2 days, right? Things like that. That's local disruptions. Global disruptions depends from sector to sector, but of course, just give you some examples. The September 11 attacks, they actually shut down all of the air traffic in North America for 2 days, but most airlines took another 3 days to get their aircraft back in the air, and that was simply because of planning, right? So because all of their airplanes were at the wrong location, and then all of a sudden they had to put them back in the air, and it took them another 2-3 days for most of them, not all of them, to deal with that. The volcano eruption, I'm not going to pronounce the name. Shut down air traffic in Europe for 8 days, so a similar situation. And again, airlines, but the COVID-19 also had a very big impact on that, right? So, but you see this in all industries, that there could be these global disruptions that really change the thing. Now, there is this thing that people say, we cannot automate because the plans will change, right? I think it's like this. We need to automate because the plans will change. Sounds strange, right? We cannot, because the plans will change from what we plan, we need to automate it, and we need to make those plans. Yeah. So, how? So there's a couple of things that typically help when you're starting to implement these cases. That if you think about those earlier, you will probably have a much better experience when you implement this in real. And the first thing you want to think about is, when is your publication deadline? So what is a publication deadline? It's basically when your plan escapes into the wild, right? It's when you tell your employees when and how they will work. And for the record, if you tell a nurse you're going to be free on Friday evening, of course, or he or she will start making plans for that Friday evening with their friends, right? So the moment you let it go, then it will be very hard to change your mind, right? So, and that's basically publication, the moment you let it go. So for example, for technician routing, can be 1 hour before the technicians depart. They don't really care where they have to travel, where they have to drive to today, as long as they're back home by 5-6 o'clock, right? School timetabling, you wanted to have that before it actually goes in, before the school actually starts. So end of the vacation, you want to have your timetable set. For security guards or nurses, this could be 4 or 6 weeks before they do the shift, sometimes 3 weeks, sometimes less, sometimes more. Depends on the country, depends on the culture, depends on a number of things. Sometimes it's set in through legal reasons or contract reasons, it's actually set in stone. Facility location, I haven't talked about that problem yet, but that's a more strategic problem on where you put certain buildings and so forth. But that's something you would do actually months before. Now, just to illustrate that, here, let's say we have a plan where the first part of that plan executes on 28 February at 8 o'clock, right? So that's the execution start, right? And of course, the planning window might be a week, might be a day, might be 5 months, 6 months, or a year, right? Depends on the case. Now, the publication of that plan could be a few hours before that, like in vehicle routing, right? And that's called operational planning. Or could be a few weeks before that, right? When you have, when you're telling employees when to show up for work, right? And it could also be months before that in far more strategic cases. So you need to know your publication date, right? How much in advance do you need to tell your plan, right? Do you need to tell them what will happen? So this is called multi-stage planning, right? So just give you some examples. In a strategic case, do we want to expand the maternity ward? In a tactical planning is, do we want to hire more more specialist with a certain skill. Operational, do you want to assign that particular shift to that particular person? So each planning stage feeds into the next, because if you don't hire more employees with certain skills, you cannot assign them to work in your operational skills and vice versa, right? But because the fact that their publication date is different, you cannot solve it as one big planning problem. You have to split them up naturally, right? Another example for trains and airplanes, you want to add a stop in Philadelphia, is strategic. You want to depart at 7 a.m. That's tactical, when your train will actually ride. And the operational one, which actual locomotive will you use, the actual thing that stands there on the track, and which maybe also who's actually going to drive that and stuff like that. So again, multiple planning problems. And so the whole point is that problems with different publication moments cannot be solved in the same solve call, cannot be solved by the same solver, but they will feed into each other, right? But they cannot be solved by the same solver. Just the rules of the universe, nothing we can do about it. Another thing to keep in mind is Conway's law, which says that any organization that designs a software system will produce a design whose structure is a copy of the organization's communication structure. Simply put, if you have Group 1 doing a planning problem and Group 2 doing a planning problem, and you know it would be better if you would just solve them as one big planning problem. First introduce automating those with TimeFault Solver here and there separately before trying to solve it all at once. Because otherwise you are solving two problems at the same time. First of all, getting it automated, getting it optimized, getting everybody comfortable with that, getting all the constraints tweaked correctly that everybody thinks this is a much better schedule than it used to be. Not just one party, but all stakeholders, right? And then the change management of actually moving these two organizations together. So keep that in mind when in your ambitions, actually do a multi-phase approach where you say, okay, first we optimize each subpart with TimeFault Solver, and then we can start bringing this together. This is not just if there are different types of planning problems, for example, assigning drivers and trains, but also in the same planning problem where you might say, okay, right now, every district organizes itself, right? But we want to pool all the districts together. That's fine. First, automate it per district. As soon as that works well, jump to pooling things together, and you will see additional benefits. If you do it in one big bang, you are going to, it's going to be much harder, and and you will deliver slowly. Typically, that's the paradox, of course. So it's much faster to deliver it in two phases. Yeah. Okay. So planning problems solved by different groups should use different solvers in the first year in production, right, or the first months in production, whatever the case may be, depending on how fast your organization deals with the change. In practice, for example, here we have train wagon and train assignments of the wagon as well as the platform. You can see here, this is something you can actually inject a solver manager into this. And this is basically when I press the green button, what we do is we call this solve method, right? So you see I have a different one for both of these, right? So the next part is assigning to time. So one of the big, like we said earlier, there was Luka showed some annotations around planning solution and so forth. Those are all always the same. You can copy those from one of the examples, and we're looking at removing that boilerplate. But the other part, what is your planning entity and what is your planning variable or variables? You might have two or more even. That's the hard part. That's where people struggle with, and it's a little bit like database design, right? The first time you create a database schema, it's not going to turn out well. You're going to learn a lot through your mistakes, right? It's very similar to this. So we've tried to, and I think we've succeeded in the manual, to actually explain a domain modeling guide to help you decide, okay, how do you want to tell the solver what should change, right? And the first question you should ask yourself is, what changes during planning, right? And that's typically your planning variable. But then you still have some 100 different ways to do it. And let me just guide you through some of the approaches that work. Right. So the first question to ask yourself is, do you assign to time? So, for example, no. Let's say the answer to that question is no. The domain lacks time data, like, for example, facility location problem or knapsack problem. I've not gone into these problems, but those are easy. Then you don't have to worry about this, obviously. But so you don't have any imports of Java time or Java util data or anything like that. But let's presume, yes, the domain has time, but planning does not assign to it. So here's a case of hospital bed planning. So what we're doing is we're taking every patient that comes into the hospital and we're assigning them a bed to live in, to sleep in for a number of days, right? Depending on how long they need. Now, in this particular implementation, we do not get to choose when the patients arrive or depart. That's already chosen in advance. The only thing we can choose in which bed they will sleep, if they will have a single room, multiple room, who else will be on that room, right? Then you have interesting constraints, like they need to be the same gender during the same night and stuff like that. And also in which ward they will sleep, how close they are to, the specialists of their disease and so forth. So in this particular case, we can see we said, okay, so the patient that has something that changes during planning, more specifically the bed we assign it to, that's the planning variable. That is what changes during planning. There's no time in here, so we don't get to change the time in here, so that's easy. These two things, the arrival date and the departure date, they're both set in stone. So easy, okay, no worries, let's continue. Oh, by the way, you've seen here that I use local date from java.time. Never ever use Java util date. That's like asking your bartender how to treat cancer. You'll get an answer, might not be the right one. Java util calendar, that's like asking your dog, right? Don't do that, right? So always use the stuff from Java time, like local date time, or maybe offset date or zone time, depending on your needs and how accurate you need to be. If in doubt, typically the local dates and local date times are the ones you definitely want to start out with until you need the more time zone sensitive or variants, which have their own challenges, not because of the implementation. The API is great simply because of how time zones work on this planet and how governments sometimes like to change them when they feel like it. So let's take a look. So what happens if, yes, my domain has to assign to time, right? And planning assigns to time. So then you want to pick a good domain model. So there's 4 or 5 different ways to do this, patterns to do this. Let's take a look at the first one is the time slot pattern. This is also the one we used for lesson scheduling, and this is also the one used for DevOps scheduling, by the way. So what this is for each of the lessons in this case, we have to choose the room and the time slot, but basically all of the lessons have the same duration. Right, so any lesson fits in any of the slots, and there's no it doesn't like it go half into a slot or it's larger than a slot. No, every lesson goes into a slot. But wait, and you can have a recess there, as you can see. You can have a break in there. That doesn't really matter. It all just works. But you might think, okay, for how can you use this for DevOps? Because a deep dive is obviously much longer than a conference talk. Well, any conference talk is limited to the conference time slots. Any deep dive talk is limited to the deep dive time slots. So it actually this pattern just works for them, right? And if they don't match, it's a hard constraint broken, and we don't have to care about the other stuff. Now, sometimes this doesn't work. For example, for meeting scheduling. So here we can see there's a number of meetings there, the stand-up, the sales meeting, the architects meeting. And some of the meetings take 15 minutes, others take an hour and 30 minutes, 30 minutes, 2 hours, right? And so one of the patterns you can use there is what we call the time grain pattern, where you say, I'm going to assign it to a particular time grain, right? So what is a time grain? Might be like, here the granularity is 15 minutes, so we could assign it to 8 o'clock, 8:15, 8:30, and so forth. Then, of course, we need some hard constraints to make sure that no 2 meetings aren't just assigned to the same time grain, but also not overlapping. So, for example, if we would assign the architects meeting into room A at the time it's assigned right now at 8:15, it would overlap with the green sales meeting, right? But they would not have the same start time. So to check that, the constraint would not check if the start time is the same, if it's the same time slot. It would actually check, okay, I have a start and end time of my green meeting, I have a start and end time of my yellow meeting, right? And I want to check if they overlap. And we have actually support for there. We have something called an overlap function which you can use, in your constraint streams, which will just check that off based on the start and end time. So, and of course, you can implement it quite easily yourself, but it's nice syntactic sugar. So, and in that case, you would penalize how much they overlap. So the problem with this is that what is your granularity, right? Is your granularity every hour? Is every 50 minutes, every 5 minutes, every minute, every second? Now, for example, let's say you're scheduling court hearings or anything like that. What you will see is that, or meetings, it doesn't matter what, no human can respond on a 1 second planning granularity, right? There's no point in telling somebody your meeting will start at 9:03, right? That's useless. You typically need to go to 15 minutes. That makes sense. But the lower your granularity, the bigger the search space is. Remember the search space we spoke in the middle? It still matters because these are still all of the options it needs to go through. And if you have a big granularity, 15 minutes is actually already quite big. If you have a planning window of weeks or months, then it really slows down the solving. So it's often not the best approach, time greens. It has scalability issues, right? What else is there? Well, the other one is called the chain through time pattern. What we're going to do there is we're not going to assign them to time. We're just going to assign each of in this case it's tasks, to a person, like Anne or Beth, to an employee, and then we're going to chain them up. We're going to say, what is the order? So we say Anne first does the purple task, then the yellow task. And based upon that decision, in which order do you do your who does it and in which order, we know when it starts. Why? Well, the first task starts when Anne starts at 8 o'clock. The second task starts when the first task is done. Oh, wait a second. What about lunch breaks? Well, it's very simple. The moment you go beyond 12 o'clock, you just add an extra hour for the lunch break, and then you continue, right? What about what if they have to travel between locations? Well, then you get a vehicle routing problem, which uses exactly this model, right? Let me see if I have an example of that. This is a more elaborate example, but in a vehicle routing problem, we will actually take into account the travel time between two locations, but it's the exact same model. So again, this chain through time pattern, as you can see, if there's lunches in there, we just break that out. If it's multi-days, then we just presume, okay, time ends at 5 o'clock and continues again the next day at 9 o'clock, and maybe there's some travel time in there we have to calculate. But you calculate your starting time from left to right. Always from left to right, from now towards the future. And as long as you do that, everything will be fine. Go one step back and everything will be one big chaos. Okay, so there's also a last pattern, the time bucket pattern. I'm not going to go into it today. Let me just show you continuous planning, and let's then continue for the how you can actually try this out on your computer. So continuous planning is, we showed an employee rostering a minute ago. In continuous planning, we need to assign 1 week, but we need to plan this multiple weeks in ahead. So this is typical for nurse rostering, security guards scheduling, any kind of employee scheduling, basically. And so what we do is, instead of just scheduling 1 week, here the week is only 4 days, but bear with me, we actually do that 3 times as long. So we have a planning window where we plan for 3 times the amount of time we have to publish, right? So we need to publish before the end of the day what will happen in 6 weeks from now, but we actually plan week 6, 7, and 8, right? And then we publish the first part. And then a week later, we publish week 7, but we plan week 7, 8, and 9, right? So we have a draft thing that we don't necessarily throw it away, but we plan this to make sure that whatever we release for the week we actually want to publish, that does not paint ourselves in a corner for the week after, right? And doing this, week after week, you basically get continuous planning, where you basically always have this moving planning window, and you nicely get a plan that you nicely follow your operations, and they know your published notice doesn't have to be before it happens, can be 6 weeks earlier, and nicely everybody has their plan nicely in advance. So, shall we see how people can use this
Yeah,
themselves?
sure. So, obviously there's a website. So you can go to timefold.ai. We're going to do that in a second. You can click the quick starts repo button. There's a README in there in the repository, and you just get to clone the repository and run the quick start. Run the quick start in Quarkus, as we've just shown you numerous times. So let's go to the website, shall we?
Yep.
Uh-huh.
Want me to do
Yeah,
this
sure,
part?
please.
A30 is fun, right?
Yeah.
So here we go. We click on this. View control. Yeah, here we go.
Right. So as you can see, there is a button in the top right corner. It's called star. It gets you to the Timefold Solver repo, and we are on strict orders here to get you to star the repo. So please, everyone, if you can, start the repo. Start the repo. Thank you very much if you like this presentation.
Yeah. Anyway, and here you go to the quick starts repo, and you can try this out. So you can clone this one. Here you have a list of all of the quick starts we support. If you scroll down, you will actually see some screenshots. This is the one you want to try. As you can see, the school time tabling one, we have it in variations with Quarkus, with Spring Boot, with Kotlin. This one should be somewhere else. We'll fix that. That will be fixed by the time this presentation goes live.
Okay.
And it's probably my mistake. And you can see for all of the other use cases, we have call centers and so forth. You can all try these out. And so the vehicle routing one we just showed, so this is the vehicle routing one with capacity. If you then click OK, I want to actually try this one, you'll get the instructions right here. If you copy paste this into a terminal, you clone it, and you run it, and you can try it out. And you click the solve button, and you can start playing with the data or with the constraints, whatever you feel like. Let's get back to this. Okay. If there's any questions, we'll happily answer them right now. Yes?
What I've seen is that you're using a static number of resources. But what, for example, if you're running a school, you have 5 classrooms,
yeah.
so you can get a feasible planning using those 5 classrooms. But if you could put the planning into 4 classrooms, you would be able to get a 50% reduction of gas.
Yes.
So how you would handle that kind of thing?
Yeah. Let me repeat the question. So the question is, what if your number of planning entities, some of these are actually dynamic? And so the example that was given was, what if you want to assign to lessons to rooms, but if you could use less rooms, then this would be better for the gas bill, for example, right? So in that particular case, I would just add a constraint that says count the number of used rooms, and please reduce that, right? But there's more interesting cases is when the entity itself is, for example, when you say, I want to send out vehicles, and but I want to minimize the number of vehicles. And so you don't know in advance how many vehicles you will need, but you do need to tell us which vehicles are available. We cannot just make vehicles for you and say, oh, we'll make big vehicles or small vehicles for you. You need to tell us, like, these are the ones you can select from. So what you then typically do is pretty much you actually create too many vehicles, and you add a constraint that says use as little as possible. The hard part there is figuring out how many vehicles to create. The guidance we usually give is, what do you think you will need? Double that, put that in the system, and it will, because if you give it too little, then you will break hard constraints and it will be useless to you. If you give it too many, then it will just solve a bit slower, but you will hardly notice, so that's typically the solution there. Good question.
But maybe I want to give a little teaser, because obviously we are actively developing Timefold Solver, and we're currently looking into all kinds of ways how you could test your hypotheses, right? So it may not even take that long until your sort of feature request makes it into the solver as just another API saying, okay, so tell me how good I can do it with as few resources really as possible. Just remove some of these resources, see if I can still do that. Yeah. So yes, it may be there in the solver one day, wink, wink.
Yeah. Any other questions? Yes?
The continuous planning
yeah.
solution, how do you solve state? If you start up the application, it still has the old planning.
Yeah, so how do you solve state for the continuous planning solution? So let me try to figure out an example. Um, so basically, you've sent a plan over to the employees, right? And I think I have maybe a slide on that somewhere. Uh, Maybe this answers your question to some degree. Let's take a look at this one. So this is a more elaborate implementation of continuous planning with some more concepts in there if you want to do it, which are useful. So what we have here is we're assigning employees to shifts, as you can see, but you can see there's a published window, right? So during that time, we've actually already told them this is what's going to happen, but it hasn't happened yet. So everything that is in the history we can forget about, nobody cares. But what's going to happen in the future? Now, what happens if somebody says, okay, but I cannot work on a certain day there, right? You've published that, you've said that, but I've fallen sick or whatever case may be. What we do in that case is what we call non-disruptive replanning. It's a separate feature than continuous planning, but we basically say we take something that is published, we want to solve it again, but don't change everything, because we don't want to call every single employee and say it's going to be something different. In fact, every change we do, we need to call the employee, ask her, are you okay that you come to work now on that day? So that's why we do non-disruptive replanning, where we just say, okay, with as little as few changes, deal with the fact that that person won't be there. Deal with these changes in the problem. So this is where the problem changes, but you still want to do a warm start from the previous solution. An even more advanced version of that is called real-time planning, where you might solve a problem during the night for, let's say, an hour or something like that, and then during the day something comes in and your entire plan is there's something broken in there. So what you then do is a warm start, where you take the new problems change, you take the warm start from the solution you already have, you take those together, and in milliseconds you can actually get back to a feasible solution, which with as little changes as possible. And so yeah, I hope that answers your question. Any other questions? Yes?
For that, do I have to remodel the whole domain, or is it just like solved with non-disruptive?
Yeah. No, you don't have to remodel the whole domain. That's the good news. For some time, you had some problems in the constraints sometimes. In the constraints, we'd fix that in, I guess, Timefold 1 or something like that.
There was a lot of fixes in Timefold, yeah.
Yeah. So basically, you don't have to remodel, but you do have to add a constraint. So the first thing you need to add is a constraint that says if something is published and you change it, then you break a medium constraint. So what is a medium constraint? It's not hard and it's not soft. It's in between. Why is it not hard? Because you can break it, right? To get to hard constraints are worse. You cannot break this. Those are the universe. So you can break it. Why is it not soft? Because it's far more important than any soft constraints. You really want to minimize the changes, regardless of what the soft impact is. In some cases, the soft impact does matter, but then you just make it a soft constraint. But in most cases, you would do this as a medium constraint. Thanks. Any other questions? Yes?
Well, I was wondering, in certain situations, there will be like 20, 30, 40 constraints, and each of them will have a weight.
Yes.
How do you say this one is more important than this one, and how do they combine it to a good score?
Yeah. So the question is, in some situations, you will have 20, 30 constraints, or even more, and how do you weight them against each other? How do you make those choices? So my first and initial advice is just put a number on it and continue and figure it out when you have it more running. So you'll tweak them a bit along the way. One thing we have, because this is a business problem, right? So whatever weight you put in it as a developer, later on, the stakeholders in the business will come talk to you and say, you need to increase this one, right? And then so the financial person will come to you and say, you need to increase the one that reduces the cost. And then the operator will come to you and say, you need to increase the one that makes my employees more happier and gives a better service, right? So you definitely don't want to be that person to have to juggle those weights. So what you do is you fill in some weights, so you can do your testing, you can do your benchmarking, and you use particularly something we called constraint configuration. So what is constraint configuration? I can maybe quickly show it on the website. Here we go. So you go to documentation, and we go to, where do we have constraint configuration? Constraint configuration. Yes, over here. So Yep. So a constraint configuration looks like this, right? It's basically a class. Here's a better example. It's basically a class. We have this in actually working for the DevOps schedule. For each of the constraints, like speaker conflict, and this is again where the constraint ID comes into play, we can actually set the weight as part of the data set. And so the conference scheduling is actually used for multiple conferences, and they don't all agree on what's important for their conference, obviously. So what they can do with this is they can actually say, okay, for my conference, I think that particular constraint is very important or not so important, and they can turn it on or off, and they can weight it higher and lower. It's exactly what I would advise you to do if you deal with 20, 30 constraints, to use this thing, the constraint configuration, such that when your stakeholders come to you, can just say, I've built a UI for you. You can move it to the right, solve it, right? You guys figure it out, do a meeting with each other, and figure out the weight where everybody's happy with. Don't make me the middleman, right?
And as Geoffrey said, this is fundamentally a business decision. It depends on what the business wants as a result of their optimization. So believe you me, this makes for fun meetings. Especially the more people in those meetings from different parts of the company, very fun, very long.
Yeah.
Then you're supposing that the business knows what it's doing.
Yes, then we presume the business knows what it's doing. Well, regardless if they know what they're doing, they have a very strong opinion on how they should be weighted. So definitely something to put in the UI. We have a benchmarker too, right? It's fully described here in benchmarking and tweaking. And so what you can do, what often helps, is if you try some different weights, show the results of those, and that will often diffuse some of those meetings, because you might say, okay, you find this constraint very important, but even if we increase the other constraints, there's barely, it barely gets worse, right? So one thing you definitely also want to do all the time is visualize your planning. You cannot send your business a JSON file and presume they'll be happy with it. You have to somehow visualize it. Excel works fine, spreadsheets work fine, maps works fine, tables like we've shown earlier in HTML work fine. You don't want to wait until the front-end developers have written a beautiful one for you, that you want to actually very early on just dump it into some rows and some columns. It can be a text file for all I care, something you can put on the screen and say, okay, this looks very much like the schedule I have before. So they can start debating about it, why it's bad, right? And they can tell you you've forgotten this constraint and that constraint, and you can add those, and then everybody's happy. Any other question? How many solutions there are for a specific problem? Yeah, or even more than 1,000. So the question is, how many solutions are there? So there's two different questions. How many potential solutions are there, and how many optimal solutions are there, right? Between the optimal solutions, you would care, of course, if there's different weights in there, right? First of all, how many solutions are there? Well, we looked at brute force, right? Remember the 10 to the power 80 number of atoms, 10 to the power 1040. Not all of those don't break hard constraints. Maybe 99% of them break hard constraints. That means if you take 1% of 10 to the power 1040, it's 10 to the power 1038. So there's still, billions of feasible solutions, right? So how many optimals are one? That's hard to tell. That depends on the use case, depends on the constraint. And basically, we don't know. That's the short answer. No, we care about delivering. So we don't care about, for the recording, we don't care about how many optimal solutions there are. We care about delivering the best possible solutions, validated by the score that our business wants, that is better than any other thing, any other solution that could be delivered in the same amount of time.
And obviously, the more CPU power you give us and the more time you give us, the more the likelihood we're actually going to give you something which is good. So give us more time, give us more CPU, you will get better results than if you don't.
Yeah. Just to give you an idea how that typically looks like, we have a best score graph here. So this is the benchmarker. This is the tool that everybody should be using and nobody is using. So where we have it here, the best score graph. Yes, this one. Is this the best score graph? Yeah, this is good. This is weird. this is not the best score graph. I have one here on this computer somewhere. It will take too long to solve. But basically, they always look like this. And I can maybe show this one. They always look like this, the green one here on the right. So what you see is in the first few seconds, your score goes up a lot. And then you see the law of diminishing returns. It gets harder and harder and harder to find a new best solution. These are actually cases where you have something in your code you can improve. And so we've added this here just to explain you. But the best score graph, you get it from the benchmarker. And it's a really interesting thing to look at once you start tweaking your implementation to get even better results. Because again, if you increase your score by 1%, this can literally mean millions for your company or organization, depending how big they are, right? So most of the time you don't wanna, most users I see don't bother with power tweaking, and that's fine. Just know it's possible there, configuration by exception. Any other questions? Yes?
If you do planning, for example, and you have a soft score,
Yes?
it might be that you're going to accumulate soft score over time. For example, you need to plan some employees,
Mm-hmm.
and you do a plan, and John needs to do some overtime that week.
Yep.
And then you need to do another planning for next week, and who is the lucky guy to do some overtime? It's John again.
Yes.
It's John again.
Yeah.
You want to reduce that.
Yeah. So the question is, what happens if you look at your planning week by week and you schedule it, and it's always the same guy who has to do the overtime, right? Well, there's a good way to deal with that. So one way is you could load in all of the shifts from in the past and put those all in the system too. That's not going to scale well, that's not going to work well. So what you do is in your constraint, you keep basically, it's like a tab or something. They have I forgot the specific name for it. But what you do is you have on the employee, like how many times he had to do overtime in the past, like a history thing. And you count that to the start of the planning window.
Or you keep a longer window, right? Like
Yes.
you remember what
Yeah.
was in the past.
Yeah, but and by keeping that tab in your constraint, you say, okay, I want to load balance the number of overtime across all of my employees, but I don't just want to do it within that week. I want to take into account all of the tabs of last week. It gets a bit more complex when you have employees that just start out, but that's basically the general gist of it. And full-time equivalents make it even more fun, but that's the gist of it. And it really works well for things like Christmas holidays and stuff like that. If you don't keep a tab on there, the employees care about the fact that they've missed 3 Christmases in a row with their family, right? Obviously.
Right.
Yeah.
So thanks for your questions. We're running out of time, unfortunately. So if you have any more questions, please, we'll be somewhere around here, so come catch us. We thank you for being here. I've been Lukas.
I've been Geoffrey.
Please remember about the GitHub stars and enjoy DevOps. Thank you.
Yeah.